The Vera Rubin Telescope didn't just photograph the sky, it caught it moving, and for a split second, the universe broke its own rules. In a stream of light no one was supposed to see, something shifted where nothing should exist. If the night sky is a live feed, not a picture, what else has been changing in the dark? Dark matter, dark energy, or worlds we never knew were there? Tonight, the sky is not a ceiling. It is a clock with hands too vast for human patience. Rubin was built to read that clock, night after night, until patterns start confessing. For centuries, astronomy advanced by collecting masterpieces, deep portraits of distant light, framed by narrow windows of time. We learned to trust what stayed put, to catalogue what returned, and to treat the rest as noise. But the universe was never obligated to hold still for our convenience. Vera Rubin Observatory arrives with a different philosophy, not one perfect image, but a disciplined rhythm. It will sweep the southern sky again and again, building a record where change is not an embarrassment, it is the measurement. In that record, every point of light becomes a sentence that can be read twice, then compared. This is where the stakes sharpen. When you watch the same galaxies, the same star fields, the same empty-looking corridors between them, you stop asking only, what is out there? You begin asking, what is governing what you see? And what is governing what you cannot see? The familiar sky becomes an instrument panel for forces that leave no glow of their own. Rubin's power is not merely its mirror or the extraordinary camera mounted behind it. Its power is the decision to make time a first-class coordinate, to let the sky accumulate evidence rather than impressions. With every return pass, the observatory will test whether a flicker is astrophysics or atmosphere, whether a shift is motion or distortion, whether a signal is rare or simply overlooked. And that is why this story lives on a knife edge. The survey will generate torrents of measurements, and each measurement must be honest. Calibration becomes a moral requirement, because the smallest bias can masquerade as a discovery. A momentary defect can imitate a transient, and a subtle blur can imitate gravity itself. Yet if the pipeline holds, if the cadence is steady and the systematics are tamed, the reward is unprecedented. A decade of revisits turns the cosmos into a searchable archive of behavior. It becomes possible to find the nearby objects that slip through twilight, to catch distant explosions at their first breath, and to watch galaxies warp under invisible mass. Some of what Rubin reveals will be immediate, almost intimate, faint bodies crossing the solar system like unreported traffic. Some will be violent and brief, arriving as sudden brightening and fading in faraway galaxies. And some will be slow, statistical, and unsettling. Minute distortions repeated across billions of shapes, hinting at a scaffolding no telescope can photograph directly. The central question is not whether the sky changes, because it does. The question is whether long, patient watching can force the unseen to leave fingerprints. Dark matter in the way light is bent, dark energy in the way distances and growth diverge, hidden worlds in the way orbits refuse to randomize. We are used to thinking of discovery as a single image, a dot circled in red, a headline, a name. Rubin proposes something harder. It proposes that the impossible might emerge only when the sky is treated as a decade-long experiment, where meaning is not in one frame, but in the difference between frames. So we begin at the simplest illusion of all, the idea that the night is stable. We follow the engineering that makes relentless revisits possible, and the data machinery that must separate reality from artifact. We track moving bodies close to home, then step outward into transients that rewrite entire galaxies in days. We map gravity's quiet signature across the cosmic web, and we test whether the universe's expansion is being pushed by something we still cannot name. By the end of this journey, the question will feel different. Not just what Rubin saw, but what it taught us to measure. When the sky itself becomes a living dataset and time becomes the signal we can no longer ignore. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Across 7 chapters, we move from a sky of stitched snapshots to a sky measured as motion, cadence, and consequence. And with each return to the same stars, we close in on the forces shaping everything we can see and everything we cannot. A small patch of stars looks ordinary, almost forgettable, until it stops behaving like a photograph. The frame is quiet at first, pinpricks of white on velvet black. Then one point shifts by a fraction, as if the sky inhales and exhales. Another brightens for seconds, then fades below the threshold of attention, leaving only the afterimage of surprise. A third is simply gone. Not eclipsed, not dimmed, just missing on the next look, as though someone erased it between breaths. We call the night sky constant because our watching has been intermittent, and because our eyes are built for patterns, not for audits. We look, we record, we move on, and we return later expecting continuity, like reopening a book to the same page. The universe does not wait for our schedules, and it changes while we look away, whether we are ready or not. What we miss is not rare in principle, only rare in our data, because the gaps are where the evidence hides. For centuries, astronomy has been a compromise between depth, width, and time, a three-way trade that no single instrument could escape. A telescope can stare deep and resolve fine detail, but it sees a narrow slice, like a straw held to the sky. Another can sweep wide and map large structure, but it sacrifices sharpness, turning faint galaxies into smudges. A third can watch fast, but only a small region, for a short window, because photons still take time to collect. That limitation is not just budget or ambition, it is geometry and physics. The larger the mirror, the more light you gather, yet the optics become harder to correct across a wide field. The longer the exposure, the deeper you reach, yet the Earth keeps rotating and the sky keeps moving. Even the atmosphere, its turbulence, its shifting temperature layers, adds a restless blur that must be averaged down. Every design choice is a decision about what you are willing to miss. Most of what we know was built from still frames stitched into a mosaic, and the seams were easy to forget. We learned to treat the sky as a map, with objects pinned in place, and with the rare moving dot marked as an exception. We built catalogues, named points, and measured slow drifts over years, turning motion into a careful accounting exercise. The method worked, but it trained us to ignore the sky's short-lived events, because short-lived events were inconvenient. There is history inside that habit. Early astronomers drew star charts by hand, and the stars seemed fixed enough to serve as navigation and calendar. The few changes that broke through, new stars, comets, sudden brightening, were recorded as omens before they became data. When photography arrived, it made the sky feel even more permanent, because a plate could freeze a night into a single authoritative image. A frozen frame is persuasive, and it quietly teaches the mind to expect stillness. Even modern observatories face the same geometry of limits, only with better detectors and faster computers. The sharper the image, the smaller the field of view, because aberrations grow toward the edges and must be corrected with complex optics. The longer the exposure, the fewer places you can revisit in a night, because darkness is finite and weather is fickle. The more nights you dedicate to one target, the more of the sky goes unmonitored, and the more events slip through unseen. So we studied deep but not wide, and wide but not fast, and fast but not deep, and we called the resulting picture complete. We found supernovae by luck, when a galaxy happened to be watched at the right moment. We found comets by persistence, scanning and rescanning the same regions until something moved. We found asteroids by repeated targeted searches, building orbits from sparse points and hope. We discovered transients, but we did not systematically live with them, so the universe looked calmer than it is. The sky is not stable, it is merely undersampled, and undersampling is a kind of illusion. Stars flare and settle, their magnetic fields snapping and reconnecting, releasing energy in minutes. Black holes feed and quiet, and the accretion disks around them can brighten as matter spirals inward. Distant galaxies flicker as gravity bends their light, because intervening mass acts like a lens that changes with alignment. Near Earth, small bodies drift through darkness until they cross the wrong line at the wrong time. Across the cosmos, brief signals carry information that fades before the next scheduled observation. And that is the cruel arithmetic of time. A supernova's early rise can reveal the size of the star and the physics of the explosion. Yet that rise can be missed in a single night. A stellar flare can expose magnetic storms that would strip atmospheres from nearby planets, yet it may last only minutes. A microlensing event can hint at an unseen object passing in front of a star, yet it may never repeat. The universe speaks quickly, and we have often listened slowly. Our instruments have been excellent at answering questions we already knew how to ask, because persistence is easier to measure than surprise. They excel at measuring what persists, what repeats, what stays put long enough to be scheduled and revisited. They struggle with what appears once, shifts quickly, or hides between visits, because those phenomena do not cooperate. The universe has learned to keep secrets in the gaps, and the gaps were built into our methods. The central mystery of this documentary begins in those gaps. What becomes visible when the gaps shrink and the sky cannot reset unseen night after night? What happens when the night is treated as a time-lapse movie, not a static map, with every frame anchored to the last? What if the most important evidence is not in the objects, but in their changes, in the way they refuse to stay still? That is the premise behind the Vera Rubin Observatory, and the premise is as much philosophical as it is technical. It is not just a bigger eye or a sharper lens or a deeper stare, though it is all of those in measured ways. It is a survey machine designed around repetition, cadence, and coverage, because time is the missing coordinate. Its job is to watch the same sky again and again, on purpose, until change becomes a dataset. Rubin is built to repeatedly image the entire southern sky, not as a special campaign, but as its default mode. Not once for a poster, and not twice for confirmation, but thousands of times, with exposures balanced between sensitivity and speed. It will return to the same regions night after night, building a record of change that is dense enough to trust. Over a decade, it aims to turn the sky into a continuous monitoring program where absence and presence are equally meaningful. In that design choice, the instrument becomes a new kind of scientific tool, and it changes the social rhythm of astronomy. Instead of selecting a few targets and studying them deeply, it treats everything as a target, from nearby rocks to distant galaxies. Instead of waiting for alerts from elsewhere, it generates alerts as a primary product, distributing them while the event is still unfolding. It does not assume what matters in advance. It measures first and sorts later, letting patterns emerge from scale. This approach changes what counts as an observation, because the single image is no longer the final unit. Each visit is a frame, and the sequence becomes the dataset, with timing as a first-class measurement. Motion is no longer a nuisance to be corrected, it is a signal to be interpreted, with direction and speed encoded in pixels. A brief flash is not an anecdote, it is a time-stamped event with context, linked to what came before and after. A disappearance is not a failure, it is a clue demanding a reason. Rubin will produce a living map of the cosmos, and map becomes an understatement. The map will not be a single image, but a layered history of brightness and position, stacked like transparent sheets of time. It will show what is constant, and it will highlight what is not, because variability becomes visible against a stable baseline. It will let astronomers ask questions that require time as a dimension, not as an inconvenience. The promise sounds straightforward, but the implication is unsettling, because it threatens our comfort with the familiar sky. If we watch everything, we will catch things we never predicted, and prediction has been our shield against confusion. If we measure change at scale, we will find patterns hidden in noise, and noise itself may turn out to be structure. If we keep the sky under continuous watch, the universe loses one of its oldest defenses, our inattention. The documentary's title makes a claim that demands explanation. The Vera Rubin Telescope captured something impossible, and the word is chosen carefully. Not impossible as in magic, but impossible under the old rules of observing, where the record was too sparse to prove what happened. Impossible because it required a kind of dataset that did not exist before, dense in time and broad in coverage. Impossible because it lived in the gaps between our snapshots, and the gaps used to erase it. To understand why that matters, we need to name what Rubin is built to reveal, and why each category depends on cadence. First are transients, events that appear and vanish on human timescales, sometimes within a single night. Supernovae ignite, peak and fade, carrying the fingerprints of stellar death in their changing spectra and light curves. Catching them early can distinguish different explosion mechanisms, and it can reveal the environment around the star. Stars flare, pulsate and erupt, exposing magnetic violence we barely sample, and turning quiet points into sudden beacons. Some transients are not explosions, but rearrangements, and their subtlety is part of the challenge. A star may dim because dust forms in its atmosphere, or because a companion passes in front, or because its surface cycles through instability. A galaxy's nucleus may brighten as matter feeds its central black hole, then fade as the supply thins. The key is not a single measurement, but the curve over time, the shape of change that points to a cause. Second are moving objects, the nearby bodies that share our solar system and announce themselves by shifting against the star field. Asteroids drift from frame to frame, and their motion is the message because it encodes distance and orbit. Some are harmless, some are hazardous, and many are simply unknown, too small and dark to be noticed without repetition. A survey that revisits the sky can find them earlier, track them longer, and reduce uncertainty, turning a streak into a trajectory. The stakes here are practical, not just philosophical, because prediction depends on early data. Near-Earth hazards are a problem of detection and timing is what cadence buys. If you see an object late, your options shrink, and your orbit estimate is fuzzy because you have too few points. If you see it early, you can predict its path and decide what to do, from continued tracking to planning mitigation. Rubin's cadence is designed to make early seeing routine, not heroic. Third are slow changes that only become obvious when measured precisely and repeatedly, because the universe also speaks in whispers. Galaxies evolve through mergers, star formation, and feedback that reshapes their structure, and those processes leave statistical signatures across populations. Variable stars change brightness in patterns that calibrate cosmic distances, because their periods relate to their intrinsic luminosities. The expansion history of the universe leaves subtle signatures in how populations change with time, and in how structures grow under gravity. But Rubin's deepest promise is not only in what flares or moves, because the most influential components may be invisible. It is in what cannot be seen directly, but can be inferred through its effects, the way wind is inferred from moving leaves. Gravity leaves fingerprints on light, bending and distorting images in ways that require enormous statistics, because the effect on any one galaxy is tiny. The faintest distortions are not visible in one galaxy, but emerge across billions, when the noise averages down. This is where dark matter enters the story, not as a guess, but as a persistent accounting problem. We cannot see it, but we can map its gravitational pull, and the map changes how we understand structure. Weak lensing slightly shears the shapes of distant galaxies, and the pattern traces invisible mass along the line of sight. To measure that pattern, you need wide coverage, sharp images, and stable calibration repeated over years, because systematic errors can mimic the signal. Dark energy enters through the same demand for scale and time, because acceleration is not measured in a single snapshot. The universe's expansion accelerates, and the evidence is distributed across many observations, each with its own uncertainties. Supernova distances, galaxy clustering, and lensing all contribute pieces, and each piece is stronger when measured uniformly. The pieces only fit when the survey is large, consistent, and temporally rich, so that comparisons are not biased by uneven sampling. Rubin is designed to sit at that intersection, where breadth, depth, and cadence reinforce each other. It aims to be wide enough to capture cosmic structure, deep enough to reach faint galaxies, and fast enough to revisit the sky relentlessly, because the signal is both spatial and temporal. That combination is rare because it is expensive, complex, and data-heavy, and because it forces engineering compromises everywhere else. Rubin's bet is that the payoff is a new view of reality, built from repetition rather than rarity. A decade of time-lapse astronomy changes the relationship between observer and sky, and it changes what discovery means. It turns discovery from a sequence of lucky nights into a systematic process, where the unusual is found by comparison to the usual. It makes the unknown more searchable, because it makes change measurable, and because measurement can be automated at scale. It also increases the chance of encountering anomalies that do not fit existing models, because the survey is not designed around our expectations. An anomaly is where mystery begins, but it is also where science is tested, because the first suspicion is always error. Most surprises will have explanations once the data is complete and the calibrations are verified. Some will be instrumental, some will be statistical, some will be astrophysical, and the sorting will be part of the work. A few may force revisions in how we think gravity works on large scales, because the universe is allowed to be stranger than our equations. The central question is not whether Rubin will find new objects, because new objects are guaranteed by sheer coverage. The question is what the full record of change will imply about the forces shaping everything, from local orbits to cosmic expansion. When we watch the entire sky change in real time for a decade, will patterns emerge that point to dark matter's true nature, beyond its gravitational outline? Will the acceleration we call dark energy look the same under constant scrutiny, or will it reveal cracks in the story? There is a second question hiding under the first, and it is almost uncomfortable in its simplicity. If the sky is a live feed, why did we accept frozen frames for so long? And what did that acceptance cost us? The answer is not laziness, it is physics and engineering and limited nights, and the reality of competing priorities. The sky is vast and time is relentless, and our instruments have always been selective, because selectivity was the only way to make progress. Rubin represents a shift from selectivity to surveillance, in the scientific sense, where surveillance means disciplined repetition. It is a commitment to observing first, interpreting later, and letting the universe set the agenda, even when the agenda is inconvenient. That shift will produce an avalanche of detections, and it will demand new ways to filter, verify, and understand. Because humans cannot review everything by hand, the machine will not just take pictures, it will generate a stream of events, and the stream will become a new kind of laboratory. In the cold open, a point moved, a flash appeared, and something vanished, and each of those changes is a different kind of message. In older astronomy, those moments might be dismissed as noise or missed entirely, because there would be no second frame in time. In Rubin's astronomy, they become the starting line for investigation, with immediate context and a history to compare against. The universe will still change while we look away, but we will look away less, and we will look back with better memory. This chapter is about the sky we never truly saw, because we never watched it continuously, and because we mistook our gaps for silence. The next step is to understand the instrument that makes continuous watching possible, and why its design is as radical as its mirror. To understand what Rubin can reveal, we first need to understand what it is: an observatory engineered to see time. We begin with the machine itself, and the idea that time is now part of the telescope. Cerro Pachon rises above Chile's coastal haze, where the air thins and the wind smooths into a steady flow. In daylight, the mountain looks austere, pale rock, sparse scrub, and long roads etched into the slope. The light is hard and clean, and the shadows fall sharply, as if the terrain has been cut from stone. At night, the same dryness becomes a kind of silence, and the sky feels close enough to touch. The Milky Way does not just appear here. It spills across the dome of darkness like a bright seam. This site is high, dry, and dark enough to make consistency a design feature rather than a lucky accident. Altitude matters because there is less atmosphere above you, and less atmosphere means fewer chances for starlight to be scattered or absorbed. Dryness matters because water vapor is a variable lens, and it also glows in infrared bands that can contaminate measurements. The Atacama region is famous for clear nights, yet the real advantage is statistical. Many usable hours spread reliably across seasons. Rubin is placed here because a decade-long survey needs repeatable nights, not occasional perfection. Long-term surveying is a different promise than a single heroic image, and it forces you to think like an engineer. You need weather statistics measured over years, not anecdotes remembered by observers. You need stable seeing, meaning the atmosphere blurs starlight in a predictable range on most nights. Seeing is driven by turbulence in layers of air at different temperatures, and those layers act like shifting glass. You need predictable access to the sky, because gaps in time become gaps in the story. The mountain itself becomes part of the instrument, and the observatory is built like a system that never stops listening. Roads, power, network links, and maintenance schedules are not background details here. They are the hidden scaffolding of a survey that treats every clear night as one more exposure in a single experiment. Even the placement of buildings and vents matters, because heat leaking into the dome can mimic bad atmosphere. Rubin is built around that idea, and Cerro Pachon is where the idea can survive. The purpose is not to look once and move on, collecting a trophy image for a press release. The purpose is to return, measure change, and build trust in patterns that only appear after thousands of repeats. That requires a telescope that is fast, wide, and sensitive at the same time, even when the atmosphere is merely good. Those goals usually fight each other, and Rubin is engineered to force a truce. The result is a machine that treats the night as a schedule of measurements, not a series of isolated moments. Start with the mirror, because light is the currency of astronomy and photons are the only payment the universe offers. Rubin's primary mirror system is 8.4 meters across, and that diameter translates directly into collecting area. More area means more photons per second, which means fainter objects become measurable in short exposures. Short exposures are the price of cadence, and cadence is the price of time. The mirror is also shaped and supported, so it holds its figure as gravity pulls in different directions. In practical terms, the mirror is a promise about signal to noise, the quiet arithmetic behind every measurement. If you gather more photons quickly, you can keep exposures brief without drowning in statistical uncertainty. Noise is not just electronics, because the sky itself has brightness from airglow and scattered moonlight. That matters because the survey is not trying to win a single deep stare. It is trying to keep moving. returning again and again before the sky changes. A large mirror alone does not make Rubin unusual, because astronomy has built giants before. Many telescopes are large, but they see the sky through a narrow window, like looking through a straw with exquisite clarity. They are built to study one target deeply, holding still for long exposures and collecting spectra in detail. Rubin is different because it tries to be big and wide together, and that combination changes everything downstream. It is closer in spirit to a census than a portrait. Wide field of view sounds simple until you try to keep it sharp, and the physics refuses to be polite. Light rays from the edge of a wide field strike optics at awkward angles, and small imperfections become obvious distortions. Aberrations grow toward the edges, and stars turn into tiny comets or smeared arcs if you do not correct them. A wide field also demands a huge, carefully aligned focal plane because the image must stay in focus across a broad area. The tolerances are unforgiving because a tiny misalignment can ripple across billions of measurements. Rubin's optical design is built to solve that geometry rather than surrender to it. The mirror system and corrector optics shape incoming light into a wide, well-corrected image that stays usable from center to edge. The goal is not only sharpness at the center, where any telescope can look good. The goal is uniform quality across the whole field, because the survey compares one night to another, pixel by pixel. In effect, the telescope is designed to behave like a calibrated ruler laid across the sky. Uniformity sounds like an aesthetic preference, yet it is actually a statistical necessity. Weak lensing signals are small, and they hide inside subtle changes in galaxy shapes. If the optics distort the field differently on different nights, the distortion can masquerade as cosmology. Rubin's design treats the field like a laboratory surface, measured, modelled, and corrected so that the same galaxy would look the same if the universe did not change. This is why big and wide is rare, and why it took decades of design evolution to make it plausible. If you enlarge the mirror, you increase weight, flexure, and thermal problems, because glass and steel respond to gravity and temperature. If you widen the field, you magnify every optical error and every calibration weakness. Doing both forces tight tolerances across glass, mechanics, and software, because the sky will be measured statistically rather than admired. The history of astronomy is full of narrow field precision, and Rubin is a deliberate break from that tradition. Even the air inside the dome matters, because warm surfaces create turbulence that blurs images from within. Thermal control is not glamorous, yet it is the difference between a crisp star and a star that wobbles into a fuzzy disk. The telescope structure must move quickly, but it must also settle without vibration, because the cadence demands speed without sacrificing precision. Motors, bearings, and control loops all have to cooperate, and the cooperation must be repeatable. In a survey like this, time lost to settling is time lost to discovery. Rubin's wide field is not a luxury. It is the survey's engine, and it dictates the rhythm of the entire night. Each exposure covers a large patch of sky, so the telescope can move on quickly and return later. Survey speed is measured by how much sky you can image to a given depth per night, under real conditions. Rubin is designed to maximize that number, because discovery lives in coverage plus repetition. The sky is vast, and the only way to make it searchable is to be systematic. There is a visual way to understand this, and it is almost cinematic. Imagine the telescope sweeping, pausing, and sweeping again, like a lighthouse that paints the sky with measured attention. The dome opens to a slice of darkness, and the instrument pivots with controlled urgency. You can picture the starlight sliding across the optics, guided into focus by glass and geometry. The night becomes a schedule, and the schedule becomes a dataset. At the focal plane sits the LSST camera, and it changes what a camera means in astronomy. It is a 3,200 megapixel instrument built for scientific measurement, not for photography or convenience. The sensor array is enormous, with detectors tiled into a single coordinated system that behaves like one giant eye. The camera is physically massive, closer in scale to a small car than to a handheld device. When it is shown in a clean room, surrounded by technicians in protective suits, it looks less like a camera and more like industrial machinery. That physical mass is not just a curiosity for a tour guide, because it affects the telescope's balance and motion. The camera has to be supported precisely, held steady against gravity as the telescope points across the sky. It must remain aligned while the instrument accelerates, stops, and slews to the next field. In a system built for cadence, stability is not optional. A tiny tilt at the focal plane can become a systematic bias repeated millions of times. The pixel count is not a brag. It is a requirement that falls out of the optical design. A wide field produces a large image circle, and you need pixels to sample it without losing detail. If you undersample, stars blur into the same few pixels and measurements become biased, especially for shape studies. If you oversample, you waste sensitivity and data volume, so the balance is engineered rather than guessed. That balance is anchored to the typical seeing because the atmosphere sets the effective sharpness. Sampling is one of those quiet concepts that decides whether a survey is merely large or truly precise. The atmosphere sets a typical blur size, and the camera must record that blur with enough pixels to measure its shape. Too few pixels and the blur becomes blocky, hiding subtle distortions. Too many pixels and each pixel receives fewer photons, making faint objects harder to measure quickly. The camera is therefore tuned to the site, as much as the site is chosen for the camera. Scale comparisons help because the number is abstract, and 3 billion pixels is hard to picture. It is like a wall of high-resolution screens showing one exposure at full detail, where you could walk along the wall and still not see the whole frame at once. It is also like taking a panorama and refusing to compress it, because compression hides faint structure at the edges of visibility. If you could print a single exposure at full resolution, it would be the size of a room, and it would still contain galaxies too small to notice at a glance. Rubin's camera is built to keep the faint and the fast in the same frame. The camera's sensors must also behave consistently, because the survey is a comparison machine. Each detector has its own quirks, its own response curve, and its own noise pattern. Those differences can be calibrated, but only if they are stable and measurable. Calibration frames, flat fields, and careful monitoring become part of the nightly ritual, even when the sky looks perfect. In a decade-long project, stability is a form of honesty. Pixel count matters for coverage and for precision, and the two are linked in a survey. It lets Rubin image a huge area while still resolving small shape distortions in galaxies. Those distortions are the weak lensing signal that traces dark matter statistically, like a fingerprint pressed into the distribution of light. The camera is therefore part of the dark matter experiment, not just a recording device. It is measuring geometry, not merely collecting scenery. Weak lensing is subtle because it is not a dramatic arc in a single image, at least not most of the time. It is a tiny, coherent stretching of many galaxies, visible only when you average over enormous samples. That is why Rubin needs billions of galaxies measured with uniform quality. The camera's job is to make those galaxies comparable, so that the average means something. When the signal is only a percent-level distortion, even small biases become dangerous. The camera also has to be stable in time, because the survey is built on differences between nights. You are not only measuring objects, you are measuring change, and change is easy to fake. Small shifts in focus, temperature gradients across the sensors, or drifting detector response can masquerade as astrophysical variability. Rubin's engineering treats calibration as a first-class product, because false change is as dangerous as missed change. The system is designed so that uncertainty is tracked, not hidden. Calibration itself has a long history in astronomy, and it has become more demanding as surveys have grown. Early photographic plates were powerful, yet they were uneven, and their sensitivity could vary across the emulsion. Modern CCDs brought linearity and repeatability, but they also brought new systematics that must be modelled. The shift from plates to digital detectors changed the culture because it made large catalogues feasible and reproducible. Rubin inherits that history and pushes it because its science depends on controlling tiny biases over vast datasets. Rubin's observing strategy is built around cadence, and cadence is a design philosophy as much as a schedule. Instead of one long exposure, it takes short exposures and repeats them, building a time series for nearly everything it sees. Short visits reduce trailing from moving objects and reduce saturation from bright stars. Repetition builds the time series that turns the sky into a movie. The survey is not only asking what is out there, but what it is doing over time. There is a visual rhythm to it, almost like breathing. The shutter opens, photons accumulate, and then the system moves on before the scene can blur. You can imagine the data clock ticking, exposure after exposure, while the dome frames a rotating slice of sky. The same patch of sky returns later, and the differences become meaningful because the method is consistent. Over months and years, the sky stops being a static map and becomes a record of behavior. Cadence is how motion becomes detectable, and this is especially true for small bodies in our solar system. An asteroid is not identified by its color or shape because in a single exposure, it is usually just a point. It is identified by its shift against background stars, a change in position that is too coherent to be noise. Two visits close together can reveal a moving point and constrain its direction. The method is simple in principle, yet it only works when you can repeat it relentlessly. More visits across nights turn that motion into an orbit, and an orbit turns a dot into a known object with a future. Once you have an orbit, you can predict where it will be next week, next year, and sometimes decades from now. That predictive power is why cadence matters for planetary defense as well as for pure curiosity. The sky is full of moving debris, and the only way to catalogue it is to watch repeatedly. Each additional observation tightens the uncertainty, like narrowing a cone of possible paths. Cadence is also how change becomes measurable in the distant universe, where motion is too slow to see directly. A supernova is not defined by one bright night, but by a rising and fading light curve that encodes the physics of an explosion. A variable star is not defined by a single measurement, but by a repeating pattern that reveals its internal structure. Rubin's schedule is designed so that many phenomena are sampled often enough to classify, not just to notice. Time becomes a diagnostic tool, not an afterthought. Classification is the difference between a surprise and a discovery. A single brightening could be an artifact, a flare, an explosion, or a mismeasured star near a detector edge. A sequence of measurements turns ambiguity into a story, because the timing and color evolution carry signatures. Some events rise in hours, others in days, and the cadence determines which stories can be read. Rubin is built to collect those signatures at scale. The exposure strategy balances depth against speed, and the balance is a deliberate compromise. Longer exposures go deeper, but they reduce how much sky you can revisit before dawn. Shorter exposures increase coverage and improve the ability to catch fast events, but they risk missing faint objects at the edge of detectability. The baseline cadence is tuned around typical sky brightness and seeing, because real nights are not laboratory conditions. Rubin's baseline cadence is tuned to catch both the faint and the fleeting, even though no single strategy can maximize everything. That compromise is also a reminder that surveys are choices, not neutral recordings. Every decision about exposure time and revisit rate shapes what becomes visible. The sky is not changing to match our schedule, so the schedule must be designed to meet the sky halfway. Rubin's promise is that the choices are made transparently and then held steady. In a project this long, consistency becomes a scientific instrument. Filters add another dimension to the dataset because brightness alone is ambiguous and color carries physical meaning. Rubin observes in multiple optical bands, sampling different parts of the spectrum from bluer to redder light. Color helps separate stars from galaxies because their spectra differ in characteristic ways. Color helps classify transients by their evolving temperatures because hot explosions start blue and cool as they expand. With multiple filters, an image becomes a rough spectrum spread across time. Color also helps estimate distance when spectroscopy is impossible at scale, and that limitation is fundamental. Spectroscopy is precise, but it is slow, and it requires targeting objects one by one. Rubin will see billions of galaxies, far more than any spectrograph could measure individually. Filters are the compromise that makes three-dimensional mapping possible. They are also a reminder that astronomy often advances through clever approximations, not perfect measurements. Photometric redshifts are the key term, and the idea is simple enough to say out loud. As the universe expands, light from distant galaxies is stretched to redder wavelengths, shifting recognizable spectral features through the filter set. By measuring how bright a galaxy is through different filters, you infer how far its spectrum has shifted. It is not as precise as spectroscopy, but it works for billions of galaxies. The power comes from scale, because small errors can average down when the calibration is controlled. The method is statistical, and that is both its strength and its vulnerability. Individual distances can be uncertain, yet the ensemble can still map large-scale structure accurately. The survey's uniformity matters again, because small calibration errors can bias redshift estimates. Rubin's design is built to keep those biases controlled so that the cosmic map does not warp. When you are measuring the universe's history, even a subtle tilt in the data can become a false narrative. Those distance estimates are essential for the central question, because dark matter and dark energy are inferred through patterns in space and time. Dark matter maps from weak lensing improve when you know roughly how far the lensed galaxies are, since lensing depends on geometry. Dark energy constraints improve when you can place galaxies and supernovae into a consistent distance scale. Rubin's filters turn images into a three-dimensional statistical survey. The colors are not decoration, they are coordinates. There is a historical echo here, because astronomy has repeatedly expanded its reach by adding dimensions. First came better angular resolution, then came spectroscopy, then came time domain monitoring, and then came wide-field digital surveys. Each step changed what questions were practical to ask. Surveys like SDSS made it normal to think in catalogues and pipelines, not only in individual observing runs. Rubin is the next step in that lineage, combining width, depth, and time into one instrument. All of this produces data at a scale that changes the culture of observing, and the numbers are not marketing, they are logistics. Rubin is expected to generate around 20 terabytes per night of raw imaging data under routine operations. That is not a special campaign or a once-a-month burst. It is the nightly baseline, repeated until the archive becomes a record of the changing sky. The data do not arrive as a trickle, they arrive as a tide. Over years it becomes an archive measured in tens of petabytes, with derived catalogues even larger. The raw images are only the beginning, because each image produces measurements of positions, brightnesses, shapes, and uncertainties. Those measurements become catalogues that astronomers will query like databases, searching for patterns rather than browsing pictures. In a sense, the telescope's true output is structured information. The archive becomes a memory of the sky, with timestamps attached. 20 terabytes per night is hard to grasp, so compare it to older observatory rhythms and older ways of working. Many telescopes produce far less because they target a few objects and take fewer images, often with long exposures and careful planning. Rubin produces more because it treats the whole sky as the target and revisits it constantly. The dataset is not a collection of pictures. It is a continuous measurement stream. It is closer to a sensor network than a traditional camera. That volume forces automation because humans cannot inspect each frame, not even a small fraction. The pipeline must calibrate images, correct for detector effects, subtract backgrounds, and detect sources quickly. It must measure shapes and brightnesses, associate detections across nights, and compare to previous visits with consistent rules. Timing matters because follow-up depends on speed, and some transients fade before sunrise elsewhere. Rubin's software is therefore part of the telescope, and the telescope is partly a computer. This is not entirely new, because astronomy has been moving toward pipelines for decades. Surveys like SDSS helped normalize the idea that data reduction could be standardized and shared widely. Rubin pushes the concept into the time domain, where speed matters as much as accuracy. When the sky changes, delays can erase the chance to understand why. The pipeline becomes an interpreter, translating raw pixels into events and probabilities. The most radical product is not the archive, but the alert stream, and it is designed to feel immediate. Rubin will issue millions of alerts per night when it sees statistically significant change in the sky. An alert is not a headline, and it is not a guarantee of novelty. It is a packet of evidence, delivered quickly enough to act on. The alert stream is the survey speaking in real time, with every change treated as a candidate story. It contains the location, the measured change, the context from past observations, and a confidence estimate that reflects noise and systematics. It may include a small cutout image showing what changed, along with measurements in multiple filters. The alert is meant to be machine-readable because no human can read millions of messages. The audience is a global network of software and telescopes listening for the rarest signals. In practice, the alerts are invitations, asking other instruments to look closer. Alerts are generated by difference imaging, where new exposures are subtracted from deep reference images built from many previous visits. What remains are the things that changed, moved, appeared, or vanished, standing out as residuals against an otherwise stable sky. This method turns the sky into a nightly audit, not a static catalogue. It also means the survey is designed to find the unexpected by default. The subtraction is a kind of spotlight, revealing only what refuses to stay still. Difference imaging has its own challenges, and they reveal how demanding precision becomes at scale. The reference image must match the new image in point spread function, background level, and alignment. If the matching is imperfect, subtraction leaves artifacts that look like false transients. Rubin's pipeline must therefore model the atmosphere and optics well enough to subtract cleanly, night after night. The goal is not merely to detect change, but to trust that the change is real. Millions of alerts are revolutionary because they invert follow-up astronomy, shifting initiative from humans to the sky itself. Instead of astronomers proposing targets and waiting for telescope time, the sky proposes targets every night. Follow-up telescopes can respond while events are still unfolding, not weeks later when the physics has faded. The system favours speed, coordination, and triage. It also favours humility, because the sky will always generate more change than we can chase. Triage becomes a scientific discipline in its own right, because attention is now a scarce resource. Most alerts will be ordinary variables, known asteroids, or instrumental artifacts that slip through subtraction. Some will be rare transients that require immediate spectroscopy or high-resolution imaging before they dim. The challenge is to classify quickly enough that the rare events are not drowned by the common ones. In the background, the pipeline is constantly asking a quiet question. Is this familiar? Or is this new? This is where machine learning enters, not as a buzzword, but as a necessity imposed by scale. Classification must happen using light curves, colours, motion vectors, and contextual catalogues that describe what is normally in that part of the sky. The system must learn what normal variability looks like in billions of sources across different observing conditions. Only then can it flag the truly anomalous, the events that might answer the central question. Even then, the final decision often belongs to follow-up observations, not to the first alert. Even then, the word anomalous is slippery, and that is part of the mystery. Some anomalies are new physics, and some are old physics in an unfamiliar regime. Some are simply rare combinations of ordinary processes, seen because the survey is finally wide enough. Rubin's alert stream is not just a discovery engine, it is a pressure test for our expectations. What will we notice when we can no longer pretend the sky is mostly quiet? Rubin's engineering choices are therefore tied directly to mystery. Survey speed makes the sky searchable in space because you can cover so much territory repeatedly. Sensitivity makes faint structure and distant galaxies measurable, even when each exposure is brief. Cadence makes time a coordinate, so that change becomes data rather than anecdote. The combination creates a new kind of astronomical dataset, and its power comes from the way the pieces reinforce each other. It is wide enough to map cosmic structure, and deep enough to reach the galaxies that carry lensing signals. It is frequent enough to catch explosions early and track moving objects reliably. It is uniform enough that subtle statistical effects can be trusted across years. The design is not about maximizing one number, but about making the numbers cooperate. Uniformity is the quiet requirement behind everything, and it is easy to underestimate until you try to measure the universe precisely. Dark matter signals in weak lensing are small compared to measurement noise and intrinsic galaxy shapes. Dark energy signals in cosmic expansion are subtle compared to astrophysical scatter and selection effects. If the survey changes its behavior unpredictably, the universe will look like it is changing when it is not. The danger is not only missing a signal, but inventing one. So Rubin is engineered like a metronome, returning to the same themes with disciplined repetition. The same sky is revisited with the same instrument, the same filters, and the same calibrations that can be tracked and corrected. The goal is not only discovery, but comparability across a decade, because trends require a stable baseline. A decade-long movie only works if the camera does not change its mind. The steadiness is what turns curiosity into measurement. There is also a human reason for the design, and it is easy to miss if you focus only on hardware. Traditional astronomy often rewards the single observer and the single target, the person who wins time on a famous telescope. Rubin rewards teams, pipelines, and shared infrastructure because the dataset is too large to own and too rich to exhaust. The discoveries will be distributed, and the questions will be asked by many groups at once. In that sense, the observatory is a commons, built to be used rather than guarded. This changes the meaning of a telescope, and it changes the feeling of the work. Rubin is not just a mirror pointed at the sky. It is a factory that turns photons into alerts and catalogues. The factory runs every clear night, whether or not anyone is watching live from the control room. The output is a public stream of change, and change is where the universe hides its secrets. The dome becomes a workshop, and the night becomes a production line of evidence. The documentary's hook returns here because the engineering exists to serve it rather than to impress. What if the night sky is not a picture at all, but a live feed, arriving with the regularity of a heartbeat? Rubin is built to treat it that way, with frames that arrive on schedule and accumulate into context. The impossible thing is not a single object, but the ability to watch everything change at once. When you can do that, even the familiar sky begins to feel unfamiliar. And the central question sharpens as the machine comes into focus, because relentless measurement has a way of exposing weak assumptions. When we watch the entire sky change in real time for a decade, what patterns will emerge from the noise? Will dark matter's invisible scaffolding show itself more clearly through lensing and structure growth? Will dark energy's fingerprint remain consistent under relentless measurement, or will it shift? If it does shift, will we recognize it as physics or dismiss it as a calibration mistake? Rubin's design does not guarantee answers, but it guarantees accountability, and that is a powerful kind of promise. If something brightens, there will be previous frames to compare with calibrations that can be traced. If something moves, there will be enough visits to fit an orbit and test predictions. If something vanishes, the pipeline will record the absence as carefully as the presence. In science, that kind of traceability is often the difference between a claim and a conclusion. This is why the camera has to be enormous, and why the field has to be wide, even when it complicates everything else. You cannot build a time-lapse of the universe with a narrow straw, because the rare events will happen elsewhere. You cannot catch rare events reliably if you only look where you expect them, because expectation is a filter. Rubin's engineering is a wager that breadth plus repetition will expose forces we cannot see. It is a wager that the universe will reveal itself through statistics, not through a single dramatic frame. The story now turns from the machine to its first targets, because the closest changes are the fastest and the easiest to miss. Before dark matter maps and cosmological parameters, there are moving points in our own backyard, crossing the star fields like silent sparks. Rubin is not only a telescope, it is a patrol, and the patrol begins with objects that share our sun. First, the closest mysteries. Objects moving through our own solar system, hidden until the cadence reveals them. Rubin's first shocks are not distant explosions. They are nearby dots that refuse to stay put, and they do it on a sky that most people assume is steady. The illusion of stillness is powerful, our eyes average motion away, yet the detector keeps a stricter ledger. In a single exposure, an asteroid is almost nothing. It is a faint point or a short streak, buried in background stars, and it rarely announces itself with drama. The photons it contributes can be counted in the dozens, sometimes fewer, and that is a thin signal to defend. On screen, it can look like a mistake, a speck that could be noise, a cosmic ray hit, or a pixel defect. Only time separates a real moving body from the detector's own small lies. Even the atmosphere participates, because turbulence reshapes starlight into shifting blobs that can mimic change. Asteroids are hard because they are small and dark, and because they move quickly across the detector. Many reflect little light, so they sit near the noise floor, where statistics and charts are always competing. At that floor, a single extra electron in a pixel can matter, and the boundary between real and random becomes a probability. Their surfaces are often carbon-rich or space-weathered, which means low albedo in plain terms. Little sunlight comes back. Space weathering is not just a poetic phrase. Micrometeorite impacts and solar wind sputtering can darken and redden surfaces over time. Even when an asteroid is physically large, a dark surface can make it behave like a small object in the data. Motion makes the situation worse. During an exposure, a fast object smears its photons across multiple pixels, diluting its brightness and lowering its signal-to-noise ratio. The same total light is there, but it is spread out, and the background noise gets more chances to interfere. That is why a moving asteroid can be harder to detect than a stationary star of the same total brightness. The star piles light into a tight point spread function, while the asteroid spreads it thinly along its path. In practical terms, the star looks like a crisp peak, while the asteroid becomes a shallow ridge. They also hide in geometry. Some spend most of their time near the sun's direction, where twilight and glare erase contrast, and where telescopes must avoid pointing for safety. That avoidance is not optional. Direct sunlight can damage optics and overwhelm sensors, so the most treacherous angles can remain undersampled. Visually, this is the washed-out edge of the sky, where the blue of scattered sunlight never quite becomes black. In that bright gradient, the faintest objects simply dissolve. The camera sees a smooth glow with subtle structure, and a dark rock has almost no leverage against it. This is not a minor inconvenience. Many of the most dangerous approach directions are sunward, because an object can come in from daytime and remain unseen until it swings into the night. The geometry is cruelly simple. If the asteroid stays close to the Sun on the sky, it hides behind the brightest lamp we have. Others hide in crowded star fields, where a moving point crosses a carpet of fixed points. In dense regions, confusion is the default, not the exception. The problem is not only that there are many stars, it is that their light overlaps, and their catalogue positions must be trusted precisely. Toward the Milky Way's plane, the image becomes almost textured. Countless stars, overlapping halos and diffraction spikes. A faint asteroid passing through can be swallowed by the background, like a moth crossing a floodlit wall. Even when it is detected, its measured position can be tugged by blended starlight, shifting the astrometry by fractions of an arcsecond. In those fields, the limiting factor is not only sensitivity, it is source confusion, the simple fact that too many things occupy too little angular space. A survey can be deep and still struggle because depth multiplies the number of background sources as well, and some hide in the seams between surveys. They move through regions that were not observed that night, or not observed deeply enough, or not observed with the right cadence. A moving object does not care about our schedules, and it can slip through gaps that exist only because we are human. Historically, asteroid discovery has been shaped by human scheduling and weather as much as by physics. A clouded week, a bright moon, or a maintenance gap can create a blind corridor in time. The early era of photographic plates made this even harsher. Each plate was precious, each field a deliberate choice, and the sky was never covered evenly. The danger is that the hardest objects to see can be the ones that matter most. A small body can be locally catastrophic, yet globally invisible until late, because it does not need to be large to be destructive. The atmosphere does not guarantee protection. It filters some sizes, but it also turns others into airbursts that spread energy widely. A city-scale impactor is not a planet killer, but it is still a civilization-level event for the people underneath it. The energy comes from speed as much as mass, and near-Earth objects arrive fast. At tens of kilometers per second, kinetic energy scales brutally, and even a modest diameter can translate into megatons. Near-Earth objects are not rare in principle. They are rare in our catalogues because our coverage has been intermittent, and because the sky is larger than our habits. For much of modern history, we have known the risk in outline, then argued over the details we could not measure. For decades, discovery relied on a patchwork of surveys with different depths, filters, and sky footprints. The result was progress, but also unevenness. Some regions were watched obsessively, while others were barely sampled. A few landmark programs changed the landscape, yet the overall picture still carried the fingerprints of limited time and limited field of view. Rubin changes the problem by treating motion as a primary signal. It does not wait for a dedicated asteroid search. It watches everything, repeatedly, with a rhythm designed for change. The survey strategy is not an afterthought. It is an instrument setting, as important as aperture or detector quantum efficiency. That design choice matters because motion is a kind of truth. A star can flare, a detector can glitch, but an orbiting body will keep shifting in a coherent way. The coherence is physical. Gravity constrains it, so motion becomes a filter that nature itself provides. The key is repetition with consistency. A single frame is ambiguous, but a sequence forces the sky to reveal what moved and how it moved. Each revisit is a question asked again, and the answer becomes harder for noise to fake. Rubin's cadence is built around revisits, often two observations of the same field separated by a short interval. That pairing is not just redundancy, it is the minimum lever arm needed to measure displacement. With that lever arm, the pipeline can estimate an on-sky velocity, and it can reject detections that do not behave like objects in solar orbit. Rubin's pipeline begins with difference imaging. A new exposure is aligned to a deep reference, then subtracted so that only change remains. The concept is simple, but the execution is unforgiving, because subtraction punishes small calibration errors. In practice, alignment is a careful mathematical fit. The system must match astrometry to fractions of a pixel and convolve images so their point spread functions agree, even when the atmosphere has changed. It also must normalize photometry, because a thin veil of cirrus can dim the entire field and leave false residuals if not corrected. The reference image is not a single photograph. It is a deep coad built from many nights, a portrait of what the sky looks like when nothing unusual is happening. Because it is deep, it contains faint background galaxies and stars that new images must match, and that richness makes subtraction both powerful and delicate. When the subtraction works, the static universe cancels out. The familiar star field fades and the leftovers become the story. It is like erasing the printed page so that only fresh ink remains. What survives subtraction is the audit trail. A transient brightens, a star varies, a rock shifts position and leaves a residual that does not match the static sky. The residual is not only detection, it is evidence that the sky has changed in a specific, measurable way. Visually, the difference frame is almost eerie. Black where stars used to be, and small positive and negative ghosts where change has occurred. A moving object can appear as a paired signature, a bright spot and a dark spot, marking where it was and where it is. In some cases, the signature becomes a short chain because the object moved enough that the subtraction leaves a more complex footprint. For moving objects, the residuals are the start, not the finish. The next step is linking detections across time into tracklets and tracks. This is where the survey stops being a camera and becomes a machine for inference. A tracklet is a short arc, usually within a night, that shows consistent motion. A track is longer, spanning multiple nights, and it begins to expose curvature from orbital dynamics. Curvature matters because it separates nearby objects from distant ones, and it distinguishes bound solar orbits from things that only look linear over short spans. Two visits close together can show a consistent displacement. Several visits across nights can lock in curvature and speed, which is where a simple line becomes a physical orbit. The orbit is not a guess, it is a fit constrained by celestial mechanics and by the measured uncertainties of each detection. This is motion linking, and it turns faint streaks into candidate trajectories. The pipeline proposes paths, then tests which ones remain physically plausible. It is an automated version of what early asteroid hunters did by hand, blinking plates and trusting their eyes. Except now, the blinking happens across billions of pixels. Plausible here means obeying gravity and geometry. The candidate must fit Keplerian motion within uncertainties, and it must not require impossible accelerations between observations. If a linkage implies a sudden turn on the sky, the algorithm treats it as a confession that something went wrong. The challenge is combinatorics. A crowded night produces huge numbers of detections, and most possible linkages are wrong. The sky is full of legitimate variability, and the subtraction process adds its own artifacts, so the raw list is always messier than the final catalogue. Every variable star, every subtraction artifact, every glint off a satellite can produce a point that looks like a detection. If you try to connect all points to all other points, the number of combinations explodes. The situation resembles a crowded airport terminal. Many travellers, many possible itineraries, and only a few that actually make sense. This is where computation becomes part of the telescope. Algorithms prune the search space, using constraints on velocity, direction, and curvature to discard nonsense before it multiplies. The pruning is conservative because missing a real object is worse than carrying a few extra candidates forward. Rubin's advantage is cadence plus depth. More visits reduce ambiguity because real objects keep moving coherently while false matches fall apart. Depth matters because faint objects are common, and the small ones dominate the population by sheer numbers. Depth matters because faint objects are common. The asteroid population rises steeply towards smaller sizes, so the survey's sensitivity determines how far down that slope we can see. Each magnitude deeper is not a small improvement. It is a step into a much larger reservoir. Cadence matters because time is a filter. A real asteroid will be in the next image where an orbit predicts, while a random noise spike will not reappear on schedule. Time also helps defeat confusion, because a moving object will slide away from a crowded background, revealing itself more clearly on later visits. The result is an orbit, not just a sighting. Once an orbit is fit, the object becomes predictable, and prediction is the core of safety. A predicted position turns the sky from a haystack into a map with a marked coordinate. An orbit is a compact summary of motion: semi-major axis, eccentricity, inclination, and the angles that specify orientation. With those elements, you can propagate the object forward, and you can also rewind it to infer where it came from. The mathematics is classical, but the implications are modern, because a future close approach can be computed years in advance. This is why millions matters. Rubin is expected to discover millions of new asteroids, not as a headline number, but as a statistical transformation. When the sample is large enough, the solar system stops being a set of anecdotes and becomes a measurable distribution. With millions, you stop guessing at the population. You measure size distributions, albedos by proxy, and orbital families with enough power to see structure. You also measure what you missed before, because the missingness itself becomes quantifiable rather than speculative. Brightness becomes a proxy for size only after you account for distance and phase angle, and even then, albedo complicates the inference. Rubin's multiband photometry helps separate dark objects from smaller bright ones, at least probabilistically. Color trends can also flag compositional groups, hinting at where in the early disk the material may have formed. With millions, rare categories become measurable rather than anecdotal. The tails of the distributions stop being empty, and the tails are where risk hides. A single unusual orbit can be dismissed as a fluke, but 100 similar ones demand an explanation. In small samples, outliers look like curiosities. In large samples, outliers become a map of the processes that create them, and those processes include the ones that deliver objects toward Earth. The statistics become a kind of reverse engineering, starting from present-day orbits and inferring the pathways that produced them. Potentially hazardous asteroids are defined by orbit and size, not by intent. They are objects whose paths come close enough to Earth to matter. The label is bureaucratic and calm, but it marks a real geometric relationship between two moving bodies. The definition is geometric, based on minimum orbit intersection distance, and it is practical rather than dramatic. It is a way of saying, this object has access to our neighborhood. Access does not mean impact, yet it means repeated opportunities for close approaches as years and decades pass. Earth crossers include several dynamical classes. Some cross Earth's orbit now, some will evolve into crossing orbits through resonances and planetary nudges. The solar system is a slow mixer, and even stable-looking orbits can be stirred over long times. Resonances are gravitational rhythms, places where repeated tugs add up instead of averaging out. In the asteroid belt, resonances with Jupiter can act like conveyor belts, pumping eccentricities until an object's path intersects the inner planets. Historically, these resonant gaps were noticed as missing bands in the belt, and they became early evidence that gravity sculpts populations, not just individual orbits. The most unsettling objects are not always the largest. A smaller asteroid can arrive with little warning if it approaches from the sun's direction. It can remain hidden until it emerges into darker sky, and by then the timeline for response has already compressed. That is a geometry problem, not a technology problem. A telescope cannot easily look near the Sun, and an object hidden in glare can remain invisible until the last moment. The sky has blind angles built into it, and Rubin reduces many blind spots without pretending to erase them all. High-inclination objects can also be difficult, because their paths cut across the ecliptic at steep angles. Traditional searches biased toward the ecliptic can miss them. When you design a survey around where you expect objects to be, you risk overlooking the ones that violate your expectations. The ecliptic is where most planets and many asteroids live, so it has always been the obvious place to look. Yet the solar system is not perfectly flat, and the exceptions can be the ones that surprise us. A steeply tilted orbit can be a fossil of past encounters, a record of gravitational scattering that never fully settled. High eccentricity objects spend most of their time far away and faint, then rush inward quickly. They are visible for a short window, then vanish again. That window is not only short, it is often inconvenient, arriving when the object sits low in twilight or crosses crowded fields. In that brief window, the object's apparent motion can be rapid, and its brightness can change quickly with distance. A missed week can mean the difference between a secure orbit and a lost object. The difference between known and unknown can hinge on a handful of nights. Rubin's repeated coverage is built for that window. It turns a brief appearance into a track that can be recovered on later nights. Recovery is not glamorous, yet it is the discipline that turns discovery into stewardship. Recovery is the quiet triumph of time-domain astronomy. The first detection is exciting, but the second and third are what turn excitement into knowledge. Each additional night tightens the orbit, and that tightening is what makes future predictions credible. The planetary defense workflow is a chain, and every link depends on speed. Detection becomes a preliminary orbit. The preliminary orbit triggers follow-up. Follow-up refines predictions. The chain is technical, but it is also social because it depends on institutions agreeing to share data quickly. This workflow has matured over decades, shaped by lessons from near misses and by the growing professionalism of survey pipelines. It is a modern form of vigilance, built from software, telescopes, and coordination. The historical arc runs from lone observers scanning plates to automated systems issuing machine-readable alerts in minutes. Rubin feeds the first link at scale. Its alerts arrive quickly enough that other telescopes can respond while the object is still observable. The timing matters because near-Earth objects can fade rapidly as geometry changes, and a candidate can become unreachable if it slips into twilight. An alert is not just a ping. It includes a position, a brightness, a timestamp, and contextual information that helps others decide whether the candidate is real. It also carries uncertainty estimates, because a coordinate without an error bar is not a coordinate you can reliably chase. A preliminary orbit is often a cone of uncertainty. Without follow-up, that cone can expand until the object is effectively lost. The expansion is not a metaphor. It is a computed region that grows as time passes and small velocity uncertainties propagate. The cone is a visualization of ignorance. Each hour that passes without new data stretches the possible positions into a widening region, and the object can slip into that growing darkness. On screen, it can be drawn as a translucent fan sweeping across the starfield, a reminder that prediction is only as good as the last measurement. With follow-up, the cone collapses into a narrow corridor. Risk assessments become more reliable, and false alarms become less frequent. The public rarely sees this quiet narrowing, yet it is the difference between a headline and a solved problem. This is where the global network matters. Rubin does not work alone because no single facility can do all follow-up for all alerts. The network is distributed by necessity, different longitudes, different weather, different instruments, so that the sky can be watched continuously. Survey telescopes find candidates. Dedicated follow-up telescopes measure positions precisely. Radar can sometimes constrain size and shape when geometry allows. When radar is possible, it is transformative because it turns a faint point into a measured distance and velocity. When radar is possible, it is transformative. A radar echo can shrink uncertainties dramatically, and it can reveal whether an object is a single body or a rubble pile binary. It can also show rotation through changing echoes, hinting at surface roughness and shape in a way optical light cannot. The system is cooperative by necessity. Rubin's role is to make the first detection early and to make it routine. Routine is the key word, because planetary defense cannot depend on luck. Routine is the key word, because planetary defense cannot depend on luck. A system that works only when someone is paying special attention is not a system, it is a hope. Rubin's promise is not that it will catch everything, but that it will catch far more, far earlier, with fewer gaps left to chance. Early detection changes outcomes even when no impact is likely. It improves ephemerides. It prevents rediscovery cycles. It builds a long baseline for future predictions. That baseline is also insurance against the subtle forces that slowly bend orbits away from simple gravitational expectations. A long baseline matters because orbital fits improve with time separation. Small errors in velocity become obvious when you compare positions months or years apart. The orbit becomes less like a sketch and more like a surveyed boundary line. It also improves science. Orbits reveal where objects came from, which resonances delivered them, and which collisions produced their fragments. The same data that protects also explains, and explanation is part of the value of watching carefully. In the main belt, Rubin will find huge numbers of smaller bodies. Many are too faint for older surveys except in targeted campaigns. The belt becomes less a list of famous names and more a statistical ecosystem, with countless members interacting through collisions and slow dynamical drift. On a visual level, this is a thickening swarm. The belt stops being a sparse set of named objects and becomes a granular population, a moving fog of minor planets. In an animation, the points multiply until the region looks alive, like dust motes in a beam of light. Those discoveries matter because the main belt is a record of formation and grinding. Its size distribution encodes billions of years of impacts. The belt is not frozen history. It is history being rewritten continuously by fragmentation, cratering, and occasional catastrophic breakups. A steep size distribution suggests relentless fragmentation, while bumps and dips can indicate specific collisional events. Even the absence of certain sizes can be a clue, implying that bodies of that scale are unstable or efficiently destroyed. In that sense, the catalogue becomes a fossil record, but one written in orbital elements and magnitudes. Families of asteroids share orbital elements because they are shards of older bodies. With enough members, you can reconstruct collisional history statistically. You can estimate when a breakup occurred by how widely the fragments have spread, and that spread is shaped by both gravitational perturbations and slow thermal forces. Historically, asteroid families were first recognized when astronomers noticed clusters in orbital element space. Rubin's scale makes those clusters sharper, and it can reveal subfamilies that were previously blended together. It can also expose interlopers, objects that share the orbit space but not the composition, by using color as an additional discriminator. Rubin's cadence also finds objects that do not fit clean categories. Some will have unusual colors. Some will have unusual light curves that hint at odd shapes. The oddities are not distractions. They are boundary conditions on how small bodies form, evolve, and sometimes fail. Color, in this context, is a spectral fingerprint in broad strokes. It can hint at composition, at space weathering, and at whether an object resembles carbonaceous, silicate-rich, or metallic material. Broadband colors are not laboratory spectra, yet they are enough to separate major types and to prioritize targets for detailed follow-up. Light curves are another kind of fingerprint. As an asteroid rotates, its brightness rises and falls, and the pattern can reveal elongation, binarity, or surface heterogeneity. A deep, repeating dip can imply a contact binary, while a complex pattern can suggest an irregular shape tumbling through sunlight. Some will be binaries, revealed through mutual events or unusual brightness variations. Some will tumble, revealing chaotic rotation states. These rotation states are not just curiosities. They can affect how sunlight-driven forces act over time. A tumbling asteroid is not rotating around a single, stable axis. It is in non-principal axis rotation, often the aftermath of collisions or close planetary encounters. The motion is mechanically richer, and it can persist for long periods because damping is slow in small, rigid bodies. The survey will also find comets, and comets complicate the story because they do not behave like inert rocks. They are mixtures of dust and volatile ices, and when they warm, they become active in ways that break simple assumptions. A comet can brighten suddenly when sunlight triggers outgassing. Volatiles sublimate, jets form, and dust expands into a coma. The coma is not a solid object, it is a cloud, and its brightness depends on how efficiently it scatters sunlight toward us. In images, the transformation is unmistakable. A star-like point grows a fuzzy halo, and sometimes a tail stretches away, tracing the pressure of sunlight and the flow of gas. The tail's direction is a diagram of forces: dust pushed by radiation pressure, ions guided by the solar wind. That activity changes the comet's brightness and can change its trajectory slightly. Non-gravitational forces can matter when jets push unevenly. The effect is small per day, but it accumulates, and that accumulation can separate a successful recovery from a frustrating miss. The effect is small per day, but it accumulates. A steady jet is like a tiny thruster, and over weeks it can shift the predicted position enough to complicate recovery. The uncertainty is not only where the comet will be, but how its activity will evolve as different ices turn on at different temperatures. Early detection is critical because comet behavior evolves quickly. If you catch the onset of activity, you can model how the coma develops and how the nucleus responds. That onset is a laboratory moment because it exposes fresh material before it is altered by repeated heating. That onset is a laboratory moment. It tells you which ices are waking up first, how porous the surface is, and whether the nucleus is sealed by a crust or fractured by vents. It also hints at internal layering, whether the comet is a uniform mixture or a patchwork of regions with different volatile inventories. A late discovery can miss the physics. The comet may already be fragmented, already depleted, already past the phase that reveals its composition. By the time it is bright and obvious, some of the most informative chemistry may have already been driven off. Comet fragmentation is not rare, and it can be sudden. A nucleus can split into multiple pieces, each with its own activity, turning a single predicted object into a small, evolving cluster. Visually, the coma can become lopsided, then separate into distinct condensations, like embers breaking apart in a draft. Rubin's difference imaging is well suited to sudden brightening. A quiet point becomes a growing, fuzzy source, and the subtraction flags it immediately. The alert arrives while the object is still changing, which is exactly when other telescopes want to look. Difference images can also highlight the coma's expansion. Instead of a clean point residual, you see a broader shape that changes from night to night, as if the object is breathing. The residual's morphology becomes data, not just a detection flag. Repeated visits then build a light curve of activity. The curve can distinguish steady sublimation from explosive outbursts. A smooth rise might indicate gradual heating and sustained jets, while a sharp spike can suggest a surface collapse or an internal pressure release. A smooth rise might indicate gradual heating and sustained jets. A sharp spike can suggest a surface collapse, a fresh patch of ice exposed, or an internal pressure release. Each pattern is a clue, and the clue matters because brightness predictions for comets are notoriously unreliable. Comets also test prediction. Their orbits can be refined, but their brightness is harder to forecast because activity depends on composition and structure. Two comets with similar orbits can behave very differently, and that difference is a reminder that small bodies are not standardized. Two comets with similar orbits can behave very differently. One can remain quiet until close to the Sun, while another can flare far out, implying more volatile ices like carbon monoxide or carbon dioxide. That uncertainty matters for follow-up planning, because spectroscopy and spacecraft tracking depend on knowing when the comet will be bright enough. That uncertainty matters for follow-up planning. Spectroscopy and spacecraft tracking depend on knowing when the comet will be bright enough. Spectroscopy is time-sensitive because the coma's chemistry changes with distance, and early measurements can capture pristine volatiles before solar heating alters the surface layers. Rubin's alerts become scheduling signals. They tell the network when to look, and they do it while the comet is still changing. In a control room that looks like a queue reshuffling in real time, targets promoted because the sky just revealed something new. Some comets will be long-period visitors, arriving from the outer reservoirs. Some will be short-period objects, shaped by repeated solar passes. Long-period comets can arrive on steep, unfamiliar trajectories, and their first approach can be their most informative. Long-period comets can arrive on steep, unfamiliar trajectories, and their first approach can be their most informative. Short-period comets, by contrast, carry the scars of many close encounters with sunlight. Rubin's decade-long baseline helps separate these populations because it finds faint inbound objects earlier and tracks them longer as they approach. The deeper tension is that the solar system is not a museum. It is a traffic system with merging lanes, resonant traps, and occasional collisions. That traffic is mostly silent, and the silence is part of what makes it unsettling. That traffic is mostly silent. Objects pass each other by millions of kilometers, yet their collective motion is shaped by the same gravitational rules that govern planets. When you visualize it, the orbits resemble layered streams, some nearly circular, some sharply elongated, interweaving without contact most of the time. Jupiter and the other planets sculpt orbits through gravity. Resonances can pump eccentricity, shifting objects from stable zones into Earth-crossing paths. Jupiter is especially influential because of its mass, and its role is ambiguous, sometimes ejecting bodies outward, sometimes steering them inward through resonant corridors. Jupiter is especially influential because of its mass. It can both shield and threaten, ejecting some bodies outward while steering others inward through resonant corridors. The same gravitational strength that clears space can also deliver projectiles, depending on the initial conditions. Small forces accumulate too. Thermal recoil can slowly drift asteroid orbits over years, nudging them toward resonant gateways. This is the Yarkovsky effect in plain terms. Sunlight warms a rotating body, and the delayed re-radiation of heat produces a tiny thrust. This is the Yarkovsky effect in plain terms. Sunlight warms a rotating body, and the delayed re-radiation of heat produces a tiny thrust. Over long times, that tiny thrust becomes a migration. It is a reminder that even in space, where everything seems frictionless, there are still subtle ways to push. Rubin cannot measure every subtle force directly, but it can provide the statistics that reveal their net effects. Population shapes become fingerprints of dynamics. If you see a depletion here and an enhancement there, you can infer transport. And if you see families spreading in semi-major axis, you can infer slow drift acting over millions of years. Millions of objects also improve impact risk models. Risk is not only about a single known asteroid, it is about the unseen population and its distribution. What fraction of objects are small and dark? How many approach from sunward directions? And how many occupy resonant pathways that feed the inner solar system? These are population questions, and they set the background rate of surprise. If you do not know how many small bodies exist, you cannot estimate how often they strike. If you do not know their orbits, you cannot estimate where they come from. The uncertainty is not just academic. It affects how societies plan, how agencies prioritize, and how seriously we take rare warnings. Rubin's catalogue reduces that ignorance, and while it does not eliminate risk, it turns risk from speculation into a quantified distribution. Quantified does not mean comfortable. It means the fear becomes a number with error bars, and that is a different kind of unease. A number can be debated, revised, and improved, yet it also forces a confrontation with reality. There is another category that carries mystery more than danger. Objects with unusual orbits can point to hidden structure in the outer solar system. Some bodies have high inclinations that do not match simple formation stories, and some have eccentricities that suggest past scattering events. In the outer reaches, the solar system's architecture becomes less tidy. The planets are far away, the orbital periods are long, and the remnants of early migration may still be written into the angles. The sky out there looks empty, yet the emptiness is partly a limitation of our detection. Some live at the solar system's edge, where sunlight is weak and discovery is difficult. They move slowly, and their faintness makes them easy to miss. A distant object can shift by only a fraction of an arcsecond per hour, and against the background, it looks almost fixed. A distant object can shift by only a fraction of an arcsecond per hour. Against the background, it looks almost fixed, and the temptation is to dismiss it as another star. Yet even slow motion becomes measurable when you revisit the same fields over years, because the shift accumulates into certainty. This is the patience of astrometry. The measurement is small, but the accumulation is relentless, and eventually the orbit emerges from the drift. Rubin's decade-long movie is essential here, because the outer solar system is a long game, and the evidence is written in tiny displacements. As these distant objects accumulate, patterns can emerge. Orbital orientations can cluster. Perihelia can align. Inclinations can show surprising coherence. The question is whether the coherence is real or manufactured by how we look. A survey's cadence, depth, and sky coverage can create apparent alignments if you are not careful. If those patterns are real, they imply a sculptor. It could be observational bias, it could be past migration, or it could be an unseen mass influencing orbits. That last possibility is the one that catches the imagination, because it suggests gravity at work beyond the catalogue. If something is out there, it would not need to glow, it would only need to pull. The evidence would be indirect, written into the directions of perihelia and the tilts of orbital planes. This is the mystery thread that points outward. The solar system's edge may be telling us that something is shaping trajectories from the dark. Rubin's role is not to declare the cause, but to provide enough objects with enough well-measured orbits to test whether the herding is statistical or physical. That requires careful accounting for selection effects. A survey sees what its cadence and depth allow, and bias can mimic alignment. Selection effects are subtle, because you are more likely to discover objects when they are near perihelion and brighter, and that preference can skew the apparent distribution of orbital angles. Rubin's uniformity helps, because consistent coverage makes biases measurable. If the survey's blind spots are known, the patterns can be corrected and evaluated. Uniformity also means comparability across years, because when the instrument, calibration, and pipeline remain stable, changes in the catalogue are more likely to reflect the sky than the system. This is where the central question echoes locally. When we watch the entire sky change in real time for a decade, hidden forces may leave measurable fingerprints. In the inner solar system, those fingerprints are risk and dynamics, and in the outer solar system, they may be hints of unseen structure. Rubin's moving object work is therefore not a side project. It is a demonstration of what time-domain surveying does to uncertainty. It turns isolated detections into trajectories. It turns trajectories into populations. And it turns populations into constraints on formation, evolution, and hazard. And it changes the psychology of the sky. The night stops being a backdrop and becomes a monitored environment with constant, silent motion. When you imagine the sky as a fixed dome, you feel safe. But when you see it as a layered flow of objects crossing and drifting, you start asking different questions. How many objects are still uncounted in the sunward glare? How many are too dark for earlier surveys? How many are passing through right now, leaving no trace in human memory? The most dangerous objects are often the hardest to see, and the hardest to see are often the ones we have not tracked yet. Rubin is built to shrink that category. It does not promise omniscience, but it replaces sporadic vigilance with systematic watching, night after night, field after field, building a map that includes motion as a first-class feature. Still, the solar system is only the nearest layer of change. Beyond it, the sky flickers for different reasons, and the timescales get shorter. The transition is abrupt, because after tracking rocks and comets across nights, Rubin begins to watch the distant universe appear and vanish in days, sometimes hours. The solar system is dynamic, but the real shock comes when the background itself starts to blink. The solar system taught Rubin to treat motion as evidence, not decoration, and that lesson scales outward fast. In our backyard, planets drift against the stars, and asteroids betray themselves by sliding a few arc-seconds between exposures. Farther out, comets grow tails and change shape, and even the sun's own output ripples in subtle cycles. Those are familiar kinds of change, and they trained astronomers to trust time as a measuring tool. Beyond the planets, the background is not a backdrop at all, because distant light sources also change. The shock is not that the sky contains rare events, but that it produces them constantly. On screen, the calm dome of night looks fixed, a velvet sphere pinned with steady points. But that stillness is an illusion, created by biology and habit. Our eyes integrate light over fractions of a second, and our memories smooth the rest. Telescopes, too, can be fooled if they only glance occasionally, because many astrophysical processes evolve between those glances. When you return night after night with the same instrument, the same filters, and the same disciplined cadence, the sky stops being a picture. It becomes a ledger of changes, and every change is a clue. Astronomers call these changes transients, meaning sources that brighten, fade, appear, or vanish on human timescales. Human timescales sounds modest, but it spans an enormous range, from milliseconds in a flare to years in a slow quasar drift. A transient can be a one-time explosion, a repeating pulse, or a flicker driven by accretion. Some transients are genuinely new light, like a supernova that was not there yesterday. Others are old objects behaving differently, like a star spot rotating into view, or a black hole's disk briefly feeding faster. The sky looks calm because our eyes average time away, and because most surveys sample too slowly. Rubin's cadence turns that hidden activity into a measurable stream. Time domain astronomy is the study of that stream, where the key data product is a light curve. A light curve is brightness versus time, often paired with color changes across filters, so you can watch temperature and opacity evolve. In practice, the light curve is not just a line on a graph, because it is a compressed story of energy flow. It records how fast an event rises, how long it plateaus, and how sharply it fades. And each phase points back to a physical timescale. Shape matters because different physics produces different rise times and fade rates. Context matters because the same light curve can mean different things in different environments. A supernova in a dusty spiral arm can look redder than the same explosion in a clean halo. A flare near a galaxy's nucleus can be a tidal disruption event, or it can be an active black hole changing state. Even within one class, viewing angle can reshape what we see, because ejecta are not always spherical and disks are not always face-on. The time domain, then, is a kind of forensic astronomy. Light curves are evidence, and the scene of the event matters. Rubin's repeated imaging makes time a coordinate, so every point on the sky gets a history. The survey does not wait for a target list, because the target list is generated by change. That inversion is subtle, but it is revolutionary, because it turns discovery into a systematic output rather than a lucky interruption. Difference imaging subtracts a deep reference from a new exposure and leaves only what moved or varied. That subtraction turns the night sky into a nightly audit of what refused to stay still. Visually, difference imaging is almost magical. You watch a dense star field dissolve into near black as if the universe has been erased. Then, in the residuals, a few bright and dark spots remain, tiny signatures of motion, variability, or imperfect subtraction. A moving asteroid leaves a paired positive and negative trail, like a ghost of its own displacement. A new supernova appears as a clean, compact point, sitting where the reference frame had nothing. In that moment, time becomes an instrument, and the instrument is tuned to change. The result is an alert stream measured in millions per night, and each alert is a hypothesis. It includes position, brightness change, timestamps, and nearby catalogue context that helps interpret it. It can also include cut-out images, small postage stamps of the sky that show the new exposure, the reference, and the difference. Those stamps are a sanity check, because subtraction can generate illusions when the atmosphere blurs, when the detector saturates, or when a bright star's diffraction spikes shift. Most alerts are ordinary variables, asteroids, or subtraction artifacts that slip through. The rare ones are the reason the system exists, and they demand speed. Speed matters because many transients evolve faster than follow-up schedules used to allow. Historically, astronomers might discover a supernova days after explosion, when the first shock signatures were already gone. Now, the earliest hours are often the most diagnostic, because they still remember the star's surface and its immediate surroundings. A supernova's first hours can reveal the size of the progenitor and the structure of its outer layers. A kilonova can fade in days, with colours shifting quickly as heavy elements form. A tidal disruption flare can rise and change as debris falls inward and reprocesses light. Rubin makes the problem feel inverted. The challenge is no longer seeing change, because change is everywhere in the alerts. The challenge is understanding what each change means, fast enough to act. In a sky that is always doing something, interpretation becomes the bottleneck. The telescope can deliver a flood of evidence, but evidence is not the same as explanation. The time domain forces astronomy to become both faster and more disciplined, because the universe does not wait for committee meetings. Supernovae are the headline transients because they are both violent and informative. They are stellar deaths that turn a star into an expanding laboratory of shock physics and nuclear reactions. For a brief time, a supernova can outshine the combined starlight of its host galaxy, and that brightness is not merely spectacle. It is energy being converted, transported, and thermalized in matter moving at thousands of kilometers per second. They also seed galaxies with heavy elements and reshape star formation through feedback. Rubin's cadence catches them earlier, when the physics is least diluted by expansion. There is also a historical echo here, because supernovae have always been time-domain events, even before the term existed. Ancient observers recorded guest stars that appeared where none had been, and then faded away. The supernova of 1054 left behind the Crab Nebula, a visible remnant that still expands today, and its pulsar ticks like a cosmic metronome. In the 20th century, supernova classification matured into a language of spectra and light curves, and that language became a tool for cosmology. Rubin inherits that tradition, but it scales it up until the exceptions become a dataset. Core collapse supernovae come from massive stars that exhaust nuclear fuel and lose pressure support. Inside such a star, fusion builds heavier and heavier elements, but iron is a dead end because fusing it costs energy instead of releasing it. When the core becomes iron-rich, it can no longer support itself with fusion, and gravity takes over. The core collapses, rebounds, and drives a shock that can unbind the star. Neutrinos carry away most of the energy, and the visible light is a smaller, delayed output. The diversity of core collapse light curves reflects different progenitors, envelopes, and circumstellar environments. That diversity is not cosmetic. It is a map of stellar life histories. A red supergiant, bloated and cool, has an extended hydrogen envelope that can produce a long plateau in brightness as the ejecta recombine. A stripped envelope star, peeled by winds or by a companion, can explode with a faster rise and a sharper decline because there is less material to trap radiation. Some core collapses may fail, producing little visible light and leaving behind a black hole, and those missing explosions are part of the story too. Rubin statistics can reveal what fraction of massive stars end quietly, because absence becomes measurable when the census is large. Some core collapse events show signatures of dense material around the star, implying strong mass loss before death. That mass loss can be driven by winds, eruptions, or binary interactions, and it reshapes the final explosion. Interaction between ejecta and that material can convert kinetic energy into light efficiently. Early bumps and narrow emission features can reveal that interaction and constrain the mass loss history. Rubin's early detections make those clues more common, not just lucky. In visuals, you might see a supernova light curve with a small early shoulder, an extra glow that lasts a day or two. That shoulder can be the shock breaking out through a dense wind, or the ejecta colliding with material thrown off months earlier. It is a reminder that stellar death is often preceded by instability, as if the star is shedding its outer layers in a final, chaotic breath. When Rubin catches that first bump, it is catching the star's last conversations with its environment. Type 1a supernovae are different, and their usefulness comes from that difference. They likely involve a white dwarf pushed toward runaway thermonuclear burning, often near the Chandrasekhar mass scale. A white dwarf is supported by electron degeneracy pressure, a quantum mechanical effect that resists compression. But that support has limits, and adding mass, through accretion or merger, can push the star into a regime where temperature and density ignite carbon explosively. The explosion synthesizes radioactive nickel, and its decay powers the light curve. The brightness is tied to how much nickel is made, which ties to the explosion conditions. The details are still debated, and the debate matters because it affects how uniform these explosions truly are. Some scenarios involve a single degenerate system, where a white dwarf accretes from a companion star. Others involve two white dwarfs spiraling together, merging in a gravitational dance that ends in detonation. There are also sub-Chandrasekhar models, where a helium layer detonates and triggers the core. Rubin's enormous sample will not settle this by rhetoric, but by patterns, rates, host environments, and subtle differences in light curve shape across galaxies. Type 1a events matter for cosmology because they can be standardized, not because they are perfectly identical. Brighter Type 1a supernovae decline more slowly, and that correlation allows a correction. This is the Phillips relation, an empirical rule that links light curve width to peak luminosity, and it is one of the quiet triumphs of observational astrophysics. Color information helps correct for dust and intrinsic variations that redden the light. After these adjustments, their peak luminosities become predictable enough to estimate distances. That predictability is not magic. It is a consequence of similar physics repeating under similar conditions. If the explosion produces more nickel, it injects more radioactive heating, and the ejectors stay hot and ionize longer, which broadens the light curve. If it produces less nickel, the light curve is narrower and dimmer, because the energy reservoir is smaller. Dust complicates this, because dust absorbs blue light more strongly than red, making objects look dimmer and redder. Rubin's multi-band photometry helps disentangle these effects, because dust reddening follows characteristic wavelength trends, while intrinsic color evolution follows the explosion's thermal history. Distance from a Type 1a supernova comes from comparing intrinsic luminosity to observed brightness. That comparison yields a luminosity distance that can be placed on the Hubble diagram. With many supernovae across redshift, the diagram traces how expansion changed over cosmic time. The logic is simple in plain language. Farther objects look dimmer, but the rate of dimming depends on how space has stretched. Rubin's contribution is volume and uniformity, which reduces selection bias and improves statistical power. Historically, this method reshaped modern cosmology. In the late 1990s, supernova surveys found that distant Type 1a supernovae were dimmer than expected in a decelerating universe. The simplest explanation was that expansion is accelerating, a result that implied dark energy or something like it. That conclusion was so unsettling that it demanded redundancy, and it still demands it today. Rubin enters this story as a machine for redundancy. More supernovae, better cadence, better calibration, and better control of the subtle biases that can masquerade as new physics. This is where transients become a ruler, not just a spectacle. A single supernova is an event, but a population becomes a measurement of geometry. The key is catching them early enough to fit light curves well and to control systematics. Early discovery reduces uncertainty in the explosion time, which improves the fit to the rise and the peak. It also improves the chance of getting spectra near maximum light, when classification is cleanest. Rubin's cadence and multi-band coverage are designed for that population science. Yet Type Ia supernovae are not the only distance tools in the time domain. Variable stars built the original distance ladder, and Rubin will measure them at unprecedented scale. Their variability is not noise, but a clock tied to stellar structure. In pulsating stars, the outer layers expand and contract, and that breathing changes temperature and radius, which changes brightness. In eclipsing systems, geometry does the modulation, as one star passes in front of another. When the clock is calibrated, it becomes a map. Cepheid variables pulsate with periods that correlate with intrinsic luminosity. The physical reason is rooted in opacity. Helium in the star's atmosphere ionizes and recombines, trapping and releasing heat in a cycle. Longer period Cepheids are larger and more luminous, so their slow pulse is a sign of a bigger engine. Measure the period, infer the luminosity, compare to observed brightness, and get distance. Cepheids anchor distances to nearby galaxies that host Type 1a supernovae, linking the ladder's rungs. Rubin's repeated imaging finds Cepheids across wide fields and improves completeness in crowded regions. In a visual sequence, you might see a nearby spiral galaxy, its arms dusted with star-forming knots. Then, as the cadence plays, a few points in those arms gently throb, bright, dim, bright again, like lanterns breathing in the dark. Those are Cepheids, and each one is a calibrated beacon once its period is measured. The power of Rubin is not that it finds one Cepheid, but that it finds them in bulk, across many galaxies, in a uniform photometric system. Uniformity matters because every mismatch in calibration can tilt the distance ladder, and small tilts become big cosmological tensions. RR Lyrae stars are older and fainter than Cepheids, and they trace ancient stellar populations. They sit on the horizontal branch of stellar evolution, burning helium in their cores, and their pulsations are shorter, often less than a day. Their luminosities are more uniform, making them useful standard candles in the Milky Way halo. Mapping RR Lyrae in large numbers reveals streams, substructure, and the galaxy's assembly history. Rubin's decade-long baseline separates true periodicity from irregular variability and improves distance precision. These variable star maps connect to the central question in a quiet way. Dark matter shapes the Milky Way's gravitational potential, and stellar streams respond to that potential. Streams are the shredded remains of globular clusters and dwarf galaxies, stretched into long filaments by tides. If streams are perturbed, the perturbations can imply clumps of dark matter passing through, like invisible stones disturbing a river. Time domain surveys supply the tracers that make those tests possible. Rubin's role is not to see dark matter directly, but to map the luminous test particles moving through its field. Kilanovae push the time domain into a new regime where light and gravity arrive together. A kilonova is the electromagnetic counterpart to a neutron star merger detected in gravitational waves. Neutron stars are extreme objects, with masses comparable to the Sun packed into a sphere the size of a city. When two of them spiral inward, they radiate gravitational waves that encode their masses and orbital evolution. The merger ejects neutron-rich material that undergoes rapid neutron capture and forms heavy elements. The radioactive decay of those freshly made nuclei powers a fast evolving glow. Kilonova light curves evolve quickly and change color rapidly, often from blue to red as opacity rises. The physics depends on ejector mass, velocity, and composition, especially the presence of lanthanides, which have complex electron structures and absorb light efficiently. In plain terms, lanthanides act like a thick fog for visible photons, pushing the emission toward redder wavelengths as the ejector cool. The event can be faint compared to supernovae and can be embedded in a host galaxy's light. Finding it is a race against fading and against the size of the gravitational wave localization region. Rubin's role is speed plus area, which is exactly what gravitational wave follow-up needs. When LIGO and Virgo report a candidate merger, the sky region can span tens to hundreds of square degrees. That region is not a neat circle, but a stretched probability map, shaped by detector geometry and noise. A wide-field survey can tile that region quickly and look for a new point source not in the reference image. Early identification enables spectroscopy and high-energy follow-up before the signal disappears. It also enables deeper imaging later, when the transient is gone, to study the host galaxy cleanly. The visual rhythm here is urgent. A gravitational wave alert arrives like a pulse on a screen, and then the camera cuts to a sky map with a broad, uncertain arc. Telescopes swivel, fields are prioritized, and images begin to stack into a search pattern. In the difference images, most candidates are mundane: asteroids, variable stars, subtraction glitches. Then one point behaves correctly. It appears where no star was. It fades quickly, and it reddens as hours pass. That is the signature of heavy elements forming in real time, far beyond any laboratory. Multi-messenger astronomy depends on coordination, and coordination depends on reliable alerts. Rubin's transient alerts can seed follow-up networks even without a gravitational wave trigger, because unusual, fast-fading events can be flagged on their own merits. Conversely, gravitational wave triggers can focus Rubin's search and prioritize fields, especially when weather or scheduling limits coverage. The combined dataset links merger rates, host environments, and heavy element production to cosmic history. It also tests whether neutron star mergers are the dominant source of certain R-process elements, a question that connects stellar death to the periodic table in our own bodies. Tidal disruption events are another kind of transient, and they reveal black holes through destruction. A star that passes too close to a massive black hole can be torn apart by tidal forces. The key idea is differential gravity. The side of the star closer to the black hole feels a stronger pull than the far side. When that gradient exceeds the star's self-gravity, the star is stretched and shredded. Roughly half the debris becomes bound and falls back, forming an accretion flow. The flare's luminosity and timescale depend on black hole mass and on how the debris circularizes. The fallback rate often follows a characteristic decline, and deviations carry information about accretion physics. In the simplest models, the rate scales roughly as a power law, reflecting how debris returns on different orbital periods. But real events are messier, because shocks, disk formation, and outflows can reprocess the radiation. If the black hole is too massive, the star can be swallowed whole with little light, setting a mass threshold for visible disruptions. If the black hole is spinning, the geometry of debris and the emission can shift, offering indirect constraints on spin. Rubin's repeated imaging finds these flares in large numbers and across diverse host galaxies. On screen, a tidal disruption event is less like a flashbulb and more like a slow bloom near a galaxy's center. The host galaxy remains, a faint smudge of billions of stars, but its nucleus acquires a new point of light. Over weeks, that point brightens, then slowly declines, sometimes with color changes that hint at reprocessing layers. The drama is hidden in the scale. This is a star being converted into a disk, into heat, into photons, and possibly into jets. The event is transient, but the black hole it reveals is permanent. TDEs also probe dormant black holes that are otherwise hard to study. Many galaxies host central black holes that are not actively accreting, so they look quiet in ordinary surveys. A tidal disruption temporarily lights them up, turning a hidden mass into a measurable transient. Population statistics then reveal how often stars wander into lost cones and how galactic nuclei are structured. Those statistics can also hint at the presence of binary black holes, because a second black hole can perturb stellar orbits and change disruption rates. Even when individual events are ambiguous, the ensemble can be decisive. Active galactic nuclei and quasars are not one-time explosions, but they are continuously variable. Their light comes from accretion disks around supermassive black holes, where turbulence and instabilities modulate emission. Gas spirals inward, heating as gravitational potential energy is converted into thermal energy, and the hottest regions emit strongly in ultraviolet and optical bands. Variability timescales relate to the size of emitting regions, because a region cannot vary faster than light can cross it. In practice, flickering becomes a ruler for the inner accretion flow. Rubin monitors AGN across the sky, building long, uniform light curves for millions of them. Those light curves enable reverberation mapping in a statistical mode, where time lags between continuum and line responses constrain broad line region sizes. The idea is conceptually simple. The central source brightens, surrounding gas responds after a delay, and the delay is a light travel distance. With enough objects, correlations between variability, luminosity, and black hole mass become measurable. Rubin's survey length matters here, because decade-long baselines allow both short-term flicker and long-term trends to be separated. Quasar variability also creates confusion, and that confusion is part of the time domain challenge. A quasar can brighten and mimic a transient in difference imaging, especially when host galaxy light is faint. Some AGN show dramatic flares that look like explosions at first glance, and some change state, dimming or brightening by large factors over months. Rubin's classifiers must use color evolution, host context, and long-term behavior to tell them apart. The difference is subtle. A supernova usually fades away to nothing, while an AGN tends to keep flickering around a baseline. But usually is not a guarantee, and the universe enjoys exceptions. Variable stars add another layer of complexity, because the Milky Way is full of them. Many stars flare due to magnetic reconnection, producing rapid brightening and color changes, especially in young or active stars. Others pulsate, eclipse, or rotate, with star spots that modulate light, producing periodic patterns that can be exquisitely stable. In crowded fields, blended starlight can create apparent variability when seeing changes, and that becomes a technical challenge in itself. Rubin's alerts will be dominated by these ordinary variables, and they are both a science target and a background. The background is not a nuisance because it encodes galactic structure and stellar physics. Variable stars trace where different populations live, from the thin disk to the thick disk to the halo. Their periods and amplitudes test models of stellar interiors, convection, and magnetic activity. But it is a nuisance for triage because it can bury rare extragalactic events. The same cadence that finds a killer nova also finds millions of periodic stars. The system must learn the difference between common rhythms and rare catastrophes. This is why the alert ecosystem exists as more than a data dump. Rubin sends alerts quickly, but it does not decide what each one is. The decision is distributed across brokers, classifiers, and follow-up teams because no single group can absorb the full torrent. The ecosystem turns raw alerts into ranked candidates and into observing plans. It also creates a shared language of probabilities, priorities, and uncertainties, which is essential when minutes matter. A broker ingests the alert stream and enriches each alert with cross-matches to catalogues. It adds information about known variables, known asteroids, host galaxies, and past measurements. It can also add environmental context, like whether the source sits in a star-forming region, near a galaxy nucleus, or along the ecliptic, where asteroids are common. It then runs machine learning models that output class probabilities and anomaly scores. The output is a prioritized list that humans and telescopes can act on. Machine learning is essential because the feature space is large and the volume is relentless. Models use light curve shape, color evolution, motion, and spatial context as inputs. They can incorporate the rate of change because a fast rise is often more informative than a bright point. They also learn instrument-specific artifact patterns, reducing false positives that would waste follow-up time. Even so, the models must be audited because bias in classification becomes bias in science. If a model is trained mostly on bright, nearby events, it may misclassify faint, distant ones, and that can quietly warp cosmological samples. Human judgment remains in the loop, but it shifts from inspection to strategy. Astronomers define what counts as interesting, then encode that into selection rules and training sets. They also chase anomalies that models cannot label confidently, because novelty often looks like error at first. In a survey this large, discovery often begins as a disagreement between a classifier and the sky. The human role becomes less about staring at images and more about designing the questions that the pipeline will ask repeatedly. Follow-up resources are limited, and that scarcity shapes the science. Spectroscopy is the gold standard for classification because spectral lines reveal composition, velocity, and ionization state. But it cannot be done for every transient because telescope time is finite and weather is indifferent. Some events will be studied deeply, while others will be characterized statistically from photometry alone. Rubin's scale forces a transition from individual case studies to population inference. That transition is not a loss of romance, but it is a change in method, and it demands careful accounting. Population inference is powerful, but it raises a new tension. If you cannot follow everything, you must trust classification probabilities and selection functions. Those functions must be measured, not assumed, or cosmology becomes fragile. A small bias in which supernovae get spectra can become a big bias in inferred distances. Rubin's uniform cadence helps because it makes selection effects more stable and more modelable. Stability is not glamorous, but it is the foundation of precision. In this chapter's arc, the universe becomes a set of time-stamped experiments. Supernovae test nuclear physics and shock propagation, and they test how stars lived before they died. Kilonovae test dense matter and heavy element synthesis under extreme conditions, and they connect to gravitational waves as a second channel of truth. TDEs test gravity and accretion when a star is shredded, and they reveal black holes that otherwise hide. AGN variability tests disk physics near event horizons, where turbulence and radiation pressure compete. Each transient is a different laboratory, and Rubin is the scheduler that never sleeps. The common thread is that transient light carries geometry and scale. The rise time sets a size scale through diffusion and expansion, because photons take time to escape thick ejecta. The color evolution sets a temperature history and an opacity history, which can indicate composition and ionization. The peak brightness, when standardized, sets a distance. Even the asymmetry of an event can leave fingerprints, because viewing angle can change observed color and decline rate. Time, in other words, is not an accessory. It is a dimension of measurement. Rubin's decade-long movie turns these events from anecdotes into statistics. It finds explosions early, classifies them consistently, and measures their rates across cosmic time. Rates matter because they connect to star formation history, metallicity, and galaxy evolution. A higher core collapse rate traces recent star formation because massive stars die young. Type 1a rates trace older populations as well, because their progenitors can take longer to ignite. The time domain becomes a census of how often the universe breaks things. That census feeds cosmology, but it also tests it. If type Ia supernovae evolve with environment, the standardization must account for it, or the Hubble diagram will bend for the wrong reason. If dust properties change with redshift, color corrections must be recalibrated, because not all dust behaves like Milky Way dust. If selection effects favor brighter events at higher redshift, the sample can look artificially uniform. Rubin's large samples enable internal consistency checks that smaller surveys could not afford. The survey can split data by host type, by local star formation, by color, and by light curve shape, and then ask whether the inferred expansion history agrees. The deeper implication is that time domain astronomy is not only about fireworks. It is about turning transient behavior into constraints on invisible parameters. A light curve can encode ejecta mass, nickel yield, and circumstellar density, even when the source is too distant for detailed imaging. A quasar's flicker can encode disk size, even when the black hole is unresolved. In the time domain, the universe reveals itself through how fast it changes. The question becomes not only what happened, but what the timing implies. Yet the more Rubin watches, the more the sky refuses to be neatly categorized. Some transients will not match known templates, and some will sit between classes, as if nature is blending mechanisms. Some will be rare viewing angles of common events, and some will be genuinely new channels. There will be supernovae with unexpected early flashes, and nuclear transients that do not fit tidy tidal disruption models. The alert stream will contain surprises, but it will also contain ambiguity. Ambiguity is not failure. It is an honest signal that the taxonomy is incomplete. Ambiguity is the real narrative tension in a live feed universe. Seeing is easy when you subtract the past from the present. Meaning is hard when the present arrives millions of times per night. Rubin's power forces a new discipline, where understanding must keep pace with detection. That discipline blends automation with skepticism, because every pipeline can be fooled and every classifier can drift. The universe is generous with data, but it is stingy with certainty. And still, even perfect understanding of luminous transients leaves a gap. Transients illuminate the universe, but they do not explain what dominates its mass. They trace expansion, but they do not explain why expansion accelerates. The next step is to follow the evidence into what does not shine. The same survey that watches stars die and black holes feed also measures subtle distortions and motions, and those point toward an unseen scaffold. Rubin can turn explosions into rulers, and rulers into a history of cosmic expansion. But the deeper mystery is written in gravitational effects without light, and in an acceleration that acts like a force. The movie of the sky is about to reveal its darkest characters, not by what they emit, but by what they make everything else do. After explosions and near misses, Rubin turns to a quieter evidence trail, because gravity leaves fingerprints even when nothing shines. Those fingerprints are everywhere, pressed into motion, bent into light, and written across the largest structures we can map. The problem is old and stubborn, and it predates modern detectors by decades of argument and recalculation. When we add up what we can see, from stars to glowing gas to dust warmed by starlight, the numbers do not work. Galaxies rotate too fast for their visible stars to hold together, at least if we use the gravity we infer from luminous matter alone. Their outer regions should fly apart, yet they keep orbiting as if extra mass is present. In a spiral galaxy, the expectation is simple in plain language, and it mirrors what we learn from the solar system. Far from the center, where most light fades, orbital speeds should drop like planets do. That expectation comes from Newtonian dynamics, where enclosed mass sets the orbital velocity at a given radius. If most of the mass sits in the bright central bulge, then the gravitational pull weakens with distance, and the orbital speed should fall. Instead, the rotation curves flatten, and they flatten in a way that is hard to dismiss as a measurement quirk. Hydrogen gas at the outskirts moves almost as fast as stars near the bright core, as though an invisible halo adds gravity where starlight runs out. Visually, you can picture a luminous pinwheel fading into darkness, while radio observations trace cold hydrogen far beyond the visible disk. The gas does not drift lazily at the edge, it races, keeping time with an unseen conductor. This was not a one-off anomaly that could be blamed on a peculiar galaxy with a messy history. Across many spirals, the same pattern repeats, and it repeats with a stubborn regularity that feels like a law. Clusters of galaxies are worse, because the scales are larger and the velocities are higher, and the bookkeeping becomes almost embarrassing. The galaxies move too quickly inside clusters, and hot gas would escape without additional gravity. The hot gas matters because it contains most of the ordinary matter in clusters, outweighing the stars by a wide margin. It shines in X-rays at tens of millions of degrees, and its temperature reveals how deep the gravitational well must be. In hydrostatic equilibrium, pressure from that hot plasma balances gravity, so the temperature becomes a kind of thermometer for mass. If gravity came only from the galaxies we can see, that gas would boil away into intergalactic space. Instead, it stays bound, held like steam trapped in an unseen pressure cooker, and the cluster persists for billions of years. The implication is blunt. Something massive is there, even if it does not radiate. Even the way clusters bend background light implies more mass than telescopes can inventory, and that inference does not depend on the gas being calm. The universe behaves as if most matter is dark. Gravitational lensing has a special authority because it does not care what matter is made of. It responds to mass itself. Stars, gas, dust, and whatever else contributes to space-time curvature. In Einstein's language, mass and energy tell space-time how to curve, and curved space-time tells light how to travel. That is a poetic summary, yet it is also a practical tool, because it turns gravity into an optical instrument. Dark matter is not a label for ignorance alone, and it is not a single desperate patch on a broken theory. It is a consistent gravitational accounting trick that repeats across scales, and it survives every attempt to make it disappear with ordinary explanations. Historically, the idea arrived in pieces, not as a single revelation that everyone accepted at once. Fritz Zwicky argued for missing mass in the 1930s using the Coma cluster, and he used the virial theorem to translate velocities into mass. His claims sounded extreme, partly because the data were crude and partly because the implication was unsettling. Later, improved measurements of galaxy rotation turned the suspicion into a crisis, because the discrepancy appeared in system after system. By the time Vera Rubin's measurements helped cement the rotation curve problem, the question had sharpened into a fork in the road. Either gravity behaves differently on large scales, or most matter refuses to glow. If most matter does not emit light, then we cannot photograph it directly, at least not the way we photograph stars. We have to map it by what it does to light and motion. That shift changes the aesthetic of the search, and it changes the emotional rhythm of the evidence. Instead of hunting a bright object, we hunt a pattern, an almost imperceptible bias in how the universe draws itself. Rubin's decade-long movie changes the strategy because it does not hunt a glow, and it does not wait for a spectacular arc. It measures distortions so small they vanish in single images. Weak gravitational lensing is the core method, and it is subtle by design rather than by accident. Foreground mass slightly warps spacetime, and background galaxy images are subtly stretched. In general relativity, the typical result is not a dramatic ring, because most lines of sight do not pass extremely close to a massive core. Instead, the sky is gently remapped, and the change is statistical rather than obvious. In plain language, gravity acts like imperfect glass, and the glass is spread across the cosmos. It does not make dramatic arcs most of the time. It nudges shapes by a fraction. Visually, imagine a sheet of transparent film laid over a photograph, then tugged in one direction until edges lean. The picture is still recognizable, yet tiny features drift together as if guided by a hidden hand. That nudge is tiny compared to a galaxy's own messy appearance, which is why weak lensing is a discipline of patience. Any one galaxy is a bad ruler because galaxies are not round. Real galaxies have spiral arms, star-forming clumps, dust lanes, and tidal distortions from past encounters, and those features do not average away in a single frame. Their shapes carry history, and that history looks like noise to a lensing analyst. The trick is statistics, and it is the same trick that turns a noisy crowd into a clear chorus. If you average over huge numbers, random intrinsic shapes cancel, and coherent lensing shear remains. Shear is the technical name for that coherent stretching, and it has a precise mathematical form. It is a two-component quantity, like a tiny arrowless vector, describing how images prefer to align along certain axes. Rubin is built for that averaging, and its scale changes what weak lensing can realistically attempt. It will measure shapes for on the order of tens of billions of galaxies across a wide sky. That number changes what is possible because weak lensing lives in the regime of small signals and large ensembles. The universe offers the effect everywhere, but it whispers rather than shouts. Sample size is not just bragging rights, and it is not only about going faint. Shear signals scale with how many independent background sources you can stack. With more galaxies, you beat down shape noise, the randomness of intrinsic ellipticities that hides the lensing imprint. In practice, the uncertainty shrinks like the square root of the number of usable sources. Consistency matters as much as depth, because a deep but unstable survey can drift into self-deception. Rubin images the same sky repeatedly, with the same camera and stable calibration discipline. The repeated cadence is not only for catching explosions, and it is not only for building a time-lapse of change. It is also for building a cleaner average image of the universe, where the atmosphere's moment-to-moment chaos becomes a measurable ingredient. Repeated visits reduce noise in multiple ways, and each way matters at the percent level. They average over atmospheric turbulence, improve signal-to-noise, and expose outliers that mimic shear. They also let the survey observe the same galaxies under different rotations of the camera and different air masses, so the sky is sampled under shifting geometry. That diversity becomes a diagnostic tool, because true cosmic shear should not care about the telescope's orientation. This is where the documentary's hook returns, because the night sky is not a picture, and it never holds still. It is a live feed that lets small effects accumulate into certainty. But weak lensing is fragile, and the fragility is the price of its power. The distortion we seek is comparable to distortions created by the telescope and the air above it. Atmospheric seeing blurs images and changes from minute to minute, and that change is not merely a loss of sharpness. That blur reshapes every galaxy, and it can imprint false alignments. In a visual sequence, the same galaxy can look crisp in one exposure and smeared in the next, as if a soft brush swept across it. The smear has a direction, and direction is exactly what lensing tries to measure. The point spread function is the key nuisance, and it is a compact way to describe a complicated reality. It is the effective shape of a point source after optics, atmosphere, and detector smear it. If the PSF were perfectly circular, it would only blur, and the analysis would be far easier. In reality, it can be slightly elliptical, and that ellipticity can vary across the field, like a subtle wind. If the PSF is slightly elliptical, it can make galaxies look slightly elliptical in the same direction, which is a dangerous coincidence. That is exactly what lensing would do. So Rubin must model the PSF across the field and across time, and it must do so with enough fidelity to avoid imprinting its own signature. Stars provide the reference, because stars should be point-like. A star, in an ideal telescope, would fall onto a single point, and it would be a perfect calibration beacon. In the real system, it becomes a tiny pattern whose shape encodes the combined behavior of air, mirrors, and sensor. PSF modeling is not a side task, and it is not merely a technical footnote for specialists. It is the difference between measuring cosmology and measuring your own instrument. This is why the narration lingers on engineering, even in a chapter about invisible matter and cosmic architecture. When the signal is a percent-level stretch, the instrument's personality becomes part of the scientific story. Detector effects add another layer, and they are less intuitive than atmospheric blur because they happen inside the camera. Charge transfer, pixel response non-uniformity, and subtle electronic crosstalk can bias shapes. As charge is read out, it can trail along columns, especially for faint sources near the noise floor. That trailing is a tiny distortion, yet it can masquerade as a preferred alignment if left uncorrected. Even small nonlinearity can matter, because weak lensing is a percent-level effect, and the required accuracy is tighter still. Precision demands errors far below that. A useful way to picture the requirement is to imagine measuring the width of a human hair from kilometers away while wind shakes your ruler. The measurement is possible in principle, but only if every systematic wobble is understood. Calibration becomes a narrative character here, because it is the bridge between raw images and physical claims. Precision cosmology is as much engineering as theory, and Rubin's design admits that openly. The calibration effort is also historical, built on lessons from earlier surveys that learned hard limits the slow way. Each generation learned that the universe is generous with photons, but stingy with clean systematics. The pipeline must propagate uncertainties honestly, because the final cosmological inference depends on how errors flow through each step. It must track how each correction changes the final shear estimate. That means uncertainty is not an afterthought added at the end, and it cannot be treated as a single number. It is carried along like a shadow, attached to each pixel, each model fit, and each catalogue decision. It must also guard against selection bias, which is a quiet way to break a beautiful analysis. If the pipeline preferentially keeps galaxies of certain sizes or orientations, shear can be biased. Even a subtle preference can matter, because lensing itself changes which galaxies are easier to detect and measure. The act of observing can become entangled with the effect being measured. Rubin's advantage is that it can test itself internally, because repetition creates controlled comparisons. With repeated observations, you can compare measurements under different seeing and rotation angles. You can also split the data, and you can do it in many ways that probe different vulnerabilities. If shear patterns change when you change the cut, that is a warning that systematics are leaking in. The survey can even create null tests, places where the signal should vanish by symmetry or by construction. When a null test fails, it points like a compass needle towards a hidden bias. Once shapes are measured and calibrated, the next step is correlation, because weak lensing is detected as a pattern across the sky. It is not a single object you can circle with a marker. Cosmic shear is the name for that pattern, and it reflects the large-scale distribution of matter along the line of sight. Nearby mass distributions shear background galaxies in correlated directions over large areas. The correlations are subtle, like a faint grain in wood that only appears when you step back and change the light. Up close, individual galaxies look chaotic, but across millions, a collective alignment emerges. From those correlations, Rubin can infer the projected mass distribution, and it can do so in multiple distance slices. The result is a map of matter, not just of light. This is the eerie part because the map reveals structure where no luminous structure exists, and it does so with mathematical calm. It is like scaffolding that guided construction and remained unseen. In visualization, the map often appears as a translucent fog laid over the starfield, with contours that rise and fall like weather. Bright galaxies sparkle like islands, while the mass field forms bridges and ridges that connect them. The cosmic web is the architecture, and the word is not metaphorical once the statistics become maps. Dark matter collapses first, forming filaments and nodes, and ordinary gas falls into those potential wells. That sequence is rooted in early universe physics, when the universe was hot, dense, and nearly uniform except for tiny ripples. Small density fluctuations, imprinted in the primordial plasma, grow under gravity, and dark matter begins clumping before atoms even form. Because dark matter does not interact strongly with light, it decouples from radiation early and starts building structure sooner. Ordinary matter is dragged along later, after photons stop pushing it around so effectively. Galaxies then form where the web is dense, and their light traces the web imperfectly, like lanterns hung on a hidden frame. Lensing traces the mass that built it. The mismatch is instructive because star formation is messy, and it is not guaranteed wherever mass exists. Gas can cool or be heated, it can be blown out by feedback, and it can hide in forms that emit weakly. Rubin can also add depth to the map, because colour is a crude distance indicator when used carefully. Multiband photometry yields photometric redshifts, placing galaxies into coarse distance slices. Photometric redshifts are not as precise as spectroscopy, yet they are powerful because they scale to billions of objects. By comparing colours across filters, you estimate how far the galaxy's light has been stretched by expansion. With slices, lensing becomes tomography, and tomography turns a two-dimensional imprint into a time-resolved story. You can watch structure grow across cosmic time by comparing shear at different redshifts. Tomography turns a flat shadow into a layered sculpture, and each layer is an epoch with its own intervening mass. The same patch of sky becomes a stack of distances, each one carrying a different imprint. Growth is the key observable, because different cosmological models predict different rates for how quickly small fluctuations become clusters and filaments. The web is not just where matter is, it is how matter got there. In the standard picture, dark energy slows the growth at late times by accelerating expansion, and that acceleration changes the competition. Gravity still pulls, but the stretching of space makes it harder for structures to assemble. Dark matter properties affect that growth as well, and they do so in scale-dependent ways that lensing can probe. If dark matter is cold, it clumps efficiently on small scales and builds many small halos. Cold, in this context, means slow-moving in the early universe, not chilly in the everyday sense. Slow particles do not stream out of overdensities, so small clumps survive and later merge into larger ones. If dark matter is warm, free streaming smooths out small-scale structure, and the early web loses its finest threads. You would see fewer small halos and less clumpiness at early times. Warm dark matter acts like a blur filter on the primordial density field, and that filter has a characteristic scale. It erases the tiniest seeds, which changes how quickly the cosmic web gains fine-grained texture. Self-interacting dark matter changes halo interiors, and it changes them without needing to rewrite gravity itself. Collisions can soften central density cusps and alter the shapes of cluster-scale halos. Those internal changes matter because lensing can probe them statistically, even when individual halos are noisy. A population of halos with rounder cores or altered concentrations leaves a detectable signature in shear profiles. Rubin cannot weigh a dark matter particle directly, and it cannot catch one in a detector buried underground. It can constrain the particle's behavior by measuring structure across many scales. This is a different kind of particle physics, conducted with galaxies as test masses and with gravity as the readout. The laboratory is the universe, and the apparatus is a survey that measures geometry and growth together. Small scales are where models diverge most, and that is where the web carries the most discriminating information. That is also where baryonic physics complicates interpretation, because gas and feedback reshape halos. Supernova explosions and black hole activity can push gas outward, changing the gravitational potential and dragging dark matter along. The result can mimic or mask the signals of different dark matter models. So Rubin's lensing program must connect to simulations, because interpretation requires controlled experiments in silico. The measured shear statistics must be compared to forward-modeled universes. Forward modeling is a discipline, and it is a kind of honesty test for the entire analysis chain. You simulate galaxies, lensing, atmosphere, optics, and detectors, then run the same pipeline as the data. The point is humility, because the easiest bias to miss is the one that flatters your expectations. Instead of assuming the analysis is perfect, you stress it with realistic imperfections, and you see whether it still recovers the truth you planted. If the pipeline recovers the input cosmology, you gain trust, and the trust is earned rather than assumed. If it fails, you learn where hidden biases live. This is the same tension as the alert stream, even though the timescales are different and the signals are quieter. The hardest signals to trust are the ones closest to the system's own imperfections. In a sense, Rubin is always looking through itself, and that is both its vulnerability and its strength. Every measurement is a negotiation between the sky's message and the telescope's translation. Lensing is one pillar, because it measures mass directly through geometry, and it does so without asking what the mass is made of. The other pillar is where galaxies are, not just how they look. Galaxy clustering measures the large-scale structure traced by luminous matter, and it is a different statistical lens on the same universe. It is a map of positions, redshifts, and patterns that emerge only in aggregate. Clustering is powerful because it encodes the initial conditions of the universe, which we believe were close to Gaussian and nearly scale invariant. Tiny early fluctuations grew into today's distribution. Those fluctuations are seen directly in the cosmic microwave background, yet clustering shows what they became after billions of years of gravitational amplification. It is the after-image of the early universe, sharpened into structure. One feature in clustering is especially valuable because it carries a physical scale that can be used like a measuring stick. Baryon acoustic oscillations leave a preferred separation scale in galaxy distributions. BAO is a standard ruler, and its origin is a specific moment in cosmic history. In the early universe, sound waves in the hot plasma set a characteristic scale before recombination froze it in. Before atoms formed, photons and baryons were tightly coupled, and pressure fought gravity in a dense, glowing fluid. That push and pull launched waves that travelled outward until the universe cooled enough for light to decouple. Later, that scale appears as a bump in the correlation function, a faint preference for galaxies to be separated by a particular distance. Measure its apparent size at different redshifts, and you measure expansion history. The bump is small, and it hides inside a much larger clustering signal that includes complex astrophysical bias. Finding it is like hearing a single repeated note inside a roaring orchestra, possible only with enormous statistics and careful control of bias. Wide-area surveys improve BAO because they reduce cosmic variance, which is the universe's own sample noise. You need huge volumes to measure a subtle bump precisely. Cosmic variance is a reminder that we only observe one universe, and we cannot rerun it with different initial conditions. Large volumes help ensure that local peculiarities do not dominate the inference. Rubin's footprint and depth make it a volume machine, and the visual scale is part of the argument. It samples enough galaxies to tighten BAO constraints across multiple epochs. The camera sweeps across thousands of square degrees, and each faint smudge becomes a data point with a distance estimate. In the mind's eye, those points assemble into a three-dimensional lattice of direction and time. Clustering also links back to lensing, and that link is where consistency tests become sharp. Lensing measures total mass, while clustering measures biased traces, and comparing them tests gravity. Bias in this context is not a moral term, and it is not an insult to galaxies. It is a technical relationship between where galaxies form and where mass actually is, and that relationship can be modelled and measured. If general relativity is correct on cosmic scales, growth and geometry should agree in specific ways, even when measured by different methods. If they disagree, something deeper is wrong. That something could be in the contents of the universe, like dark energy, or in the rules of gravity themselves. Either way, the discrepancy would be a clue carved into the cosmic web. This is where the stakes rise, because the missing mass problem and the acceleration problem sit side by side in the same datasets. Dark matter explains missing mass, but it does not explain why the universe's expansion accelerates. Acceleration is a separate mystery, and it arrived historically as a shock rather than a slow drift of opinion. Supernovae suggest it. Bayo supports it. The cosmic microwave background implies it when combined with late-time data. The combination is important because each probe has different degeneracies, and those degeneracies can masquerade as certainty. Together, they triangulate the expansion history, and the result points to a component that behaves like negative pressure. Yet the details do not align perfectly, and the misalignment has become one of the most discussed features of modern cosmology. Measurements of structure growth and measurements of expansion history show tensions that refuse to disappear. A tension is not automatically a revolution, but it is not nothing either, and it deserves careful attention. It is a persistent mismatch between datasets that should agree if the model and the measurements are both complete. Some tensions could be systematics, and the list of suspects is long because the measurements are hard. Calibration errors, photometric redshift biases, and selection effects can shift inferred parameters. Photometric redshifts are especially delicate because a small bias in distance estimates can move galaxies between tomographic bins. That, in turn, changes the inferred growth rate and the amplitude of lensing. Some tensions could be new physics, and the possibilities are constrained but still open. A changing dark energy equation of state, modified gravity, or unexpected neutrino properties could alter growth. These possibilities are not interchangeable, and they do not leave identical fingerprints across the data. Some change the geometry of distances, while others change how quickly matter clumps, and Rubin is designed to measure both. Rubin sits at the intersection, and it is built to keep the two sides of the story in the same frame. Its lensing maps measure growth, its clustering and BAO measure geometry. Together, they test consistency. Consistency is the quiet judge of cosmology, and it is often more persuasive than any single dramatic detection. When independent measurements converge, the model gains credibility, and when they diverge, the universe is asking for a new story. If Rubin finds less clustering than expected, it could imply stronger late-time acceleration or suppressed growth from particle physics. If it finds more, the opposite. Either result would ripple outward, because the parameters are connected and the inferences are entangled. Change the growth and you change the inferred matter density, the amplitude of fluctuations, and the allowed behavior of dark energy. The cosmic web becomes a diagnostic, not just a picture, and its details become testable predictions. Its thickness, connectivity, and evolution encode the rules that shaped it. In images, filaments appear like faint tendrils between clusters, and voids open like dark lakes in the galaxy distribution. In statistics, those same features become correlation functions, power spectra, and higher-order measures. Rubin's decade matters again, and not only because more years means more galaxies and deeper stacks. Time is for repeated calibration, stable systematics control, and long baselines for consistency tests. A decade also means seasonal repetition, with the same fields revisited under similar geometries as Earth loops around the Sun. That repetition helps disentangle true sky signals from subtle drifts in the instrument. The survey's uniformity is a weapon against doubt, and it is a design choice that shapes everything downstream. When every field is observed with the same strategy, selection functions become measurable. Uniformity sounds mundane, yet it is transformative, because it turns unknown biases into quantities you can bound. It means that when you see a pattern, you can ask whether it follows the sky or follows the survey. That measurability is what precision cosmology needs, because precision without accountability is just decoration. You cannot correct a bias you cannot describe, and you cannot describe a bias without uniform data. Still, the map will not be perfectly clean, and the narration does not pretend otherwise. Bright stars create scattered light and diffraction patterns that contaminate shape measurements. On screen, those stars bloom into spikes and halos, and the halos wash across faint galaxies like fog over distant city lights. The contamination is not random, so it must be modelled or masked with care. Blending is another enemy, and it grows worse as the survey goes deeper and the sky becomes crowded. In deep images, galaxies overlap, and deblending errors can create artificial alignments. As the survey goes deeper, the boundary between two galaxies can be ambiguous, like two shadows crossing on a wall. A small mistake in separating them can bias both their shapes and their measured colours. Rubin's resolution is limited by the atmosphere, and that limitation forces careful algorithms and sober decisions. It forces conservative cuts that trade quantity for reliability. Those cuts must be justified, because every removed galaxy is lost statistical power, and every kept galaxy is potential bias. If you remove too many galaxies, you lose statistical power. If you keep too many, you import bias. The decision is not purely technical, and it is not merely about computational convenience. It shapes which parts of the universe become legible, and which remain too uncertain to use in a precision test. The engineering choices become philosophical, because they define what counts as evidence when the target is invisible. What does it mean to claim a detection of dark scaffolding if your measurement depends on modelling every imperfection? The answer is not blind faith in models, and it is not the pretense that systematics can be wished away. It is a layered argument built from redundancy, cross-checks, and the refusal to accept a result that cannot survive stress. Rubin's answer is redundancy, and it is built into the observing plan rather than bolted on later. It measures the same sky in multiple filters, under many seeing conditions, across thousands of nights. Multiple filters also help separate galaxies by distance and type, which strengthens the tomography and strengthens the null tests. Color carries information about stellar populations and redshift, and that information feeds directly into lensing. It also invites cross-checks with other surveys, because no single instrument should be the final judge of a subtle signal. Space telescopes avoid atmospheric blur, and microwave lensing maps mass with different systematics. The point of cross-checks is not competition, and it is not a race for prestige. It is convergence, because the most convincing detection of the invisible is one that appears through different windows of physics. Agreement across methods is the real standard, and it is the standard that turns suspicion into knowledge. If independent instruments see the same shear patterns, the scaffold becomes hard to deny. As the maps sharpen, a new kind of unease grows, because the luminous universe looks like decoration on top of a deeper structure. The stars feel less like the main event and more like a tracer die. Galaxies are not placed randomly, and the pattern is too coherent to be aesthetic coincidence. They are beads on filaments, knots at intersections, and emptiness in the voids. That pattern is not merely pretty, and it is not merely a triumph of visualization. It is the fossil record of gravitational growth, and it encodes how matter moved when the universe was younger and denser. The voids matter too, and they are not simply blank spaces between the interesting parts. Their sizes and shapes respond to the same physics, and they provide additional tests of growth and expansion. Voids are often treated as absence, yet they are dynamical regions with their own flows and boundary walls. Their expansion and their lensing signatures can reveal whether gravity behaves as expected in low-density environments. Rubin's data turns the cosmic web into a measurable object, and that shift is the chapter's quiet climax. It is no longer a metaphor. It is a set of statistics with error bars. Those error bars are not just bookkeeping, and they are not a bureaucratic add-on to a beautiful map. They determine whether attention is a fluke, a systematic, or the first crack in a long-standing model. Those statistics are where dark matter models live or die, because models predict not only the mean web, but its texture. Cold dark matter predicts a specific hierarchy of halos and subhalos. In that hierarchy, small halos form first and merge into larger ones, leaving behind substructure like knots in a rope. Lensing can detect the aggregate effect of that substructure, even when the subhalos host few stars. Warm dark matter predicts a cutoff, and that cutoff changes the abundance of small halos and the sharpness of early filaments. Self-interacting dark matter predicts altered inner profiles and different merger behaviors. Each model changes the web in a slightly different way: how sharp the filaments are, how concentrated halos become, and how much small-scale texture survives. The differences are subtle, yet subtle is what Rubin is built to measure. Rubin will not deliver a single dramatic image that settles the debate, and it will not end with one cinematic reveal. It will deliver a convergence of constraints that narrows the viable space. That convergence is the modern style of discovery, and it matches the scale of the question. Instead of one photograph, you get a tightening ellipse in parameter space, and the ellipse tells you which stories the universe will no longer allow. That is the documentary's shift in tone, because the impossible thing is not a bright flash or a single spectacular event. It is a persistent, coherent pattern extracted from noise. And the pattern points to a deeper question, one that sits behind the scaffolding like an engine behind a wall. If dark matter is the scaffolding, what is driving the expansion to accelerate? The universe's structure is one mystery, its expansion history is another, and the two are entangled in the same data. When you change the expansion rate, you change distances, and distances change lensing geometry and the apparent strength of shear. When you change growth, you change how much mass clumps, and clumping changes the shear amplitude. Rubin's maps may show whether the engine is constant, like a cosmological constant, or whether it behaves more like a field with dynamics. They may also show whether it changes with time. A constant engine would fit the simplest interpretation, yet simplicity is not a guarantee, and history warns us about easy answers. If the data hint at evolution, then the universe is telling us that acceleration has a history. In the end, the chapter's mood remains deliberately unsettled, because the measurements are precise and the implications are enormous. We are mapping something we cannot see, and we are using that map to interrogate the fate of everything we can. Transition. If dark matter is the scaffolding, dark energy is the engine, and Rubin's decade-long movie must test both at once. The sky has been teaching Rubin one lesson for 5 chapters, and it is not a poetic lesson. Time is not decoration, not a backdrop for pretty images, but a measurable axis that turns scattered photons into physical law. When light arrives late, stretched and thinned, it carries a record of how space itself behaved while that light was travelling. In the visuals, time is written as layers. A nearby galaxy looks crisp and crowded with resolved stars, while a distant one is smaller, redder, and softened by the atmosphere. The farther we look, the older the light becomes, so every deep survey is also a history book, page by page, epoch by epoch. Dark matter was the scaffolding, mapped through distortions too small to see by eye. Now the story reaches the engine, because the universe is not just expanding, it is speeding up. Acceleration sounds like a simple word, but in cosmology it is a verdict about the future. If expansion accelerates forever, galaxies slide beyond reach and the observable universe slowly thins into darkness. If acceleration weakens or changes sign, the ending changes with it, and the physics behind that change becomes the central mystery. For most of the 20th century, the default expectation was deceleration. Gravity, acting on matter, should slow the expansion like a ball thrown upward slows under Earth's pull. That intuition is so strong that the first evidence against it felt like an error before it felt like a discovery. The first clue arrived as an insult to expectation, and it arrived in the form of dying stars. Distant Type 1a supernovae looked dimmer than they should in a universe that slows down. Dimmer meant farther than predicted, and farther meant the expansion history was not behaving as the simplest picture demanded. The observation is simple to say and hard to trust, because it depends on turning a violent explosion into a measuring stick. A Type 1a supernova begins when a carbon-oxygen white dwarf is pushed toward instability, often by mass transfer from a companion. Near the Chandrasekhar limit, thermonuclear burning runs away, and the star unbinds in seconds, forging nickel and iron that later power the light. In the footage, the physics becomes a curve. The light rises quickly, peaks, and then fades in a characteristic way as radioactive nickel decays to cobalt and then to iron. That decay chain sets the energy budget, while the expanding debris sets how quickly the light can escape. You standardize a Type 1a supernova's peak brightness using its light curve width and its color, because brighter events tend to fade more slowly. This is the Phillips relation in practice, a correlation discovered in the early 1990s that turns supernovae into standardizable candles. You compare expected luminosity to observed flux, and distance falls out, once you account for dust and for the instrument's calibration. The distance you infer is not a ruler you hold up to the sky, but a luminosity distance, defined by how light spreads through expanding space. Flux drops as 1 over distance squared, but cosmology adds extra factors because photons are redshifted and arrival times are stretched. Those effects are small nearby and decisive at high redshift, which is why distant supernovae are so powerful. Then you place those distances against redshift, the stretching of light by expansion. Redshift is not merely a Doppler effect from motion through space, but a record of space itself expanding while the photon is in flight. In a decelerating universe, the distance redshift curve bends one way, because the expansion rate was faster in the past and has been slowing. If something pushes back against gravity, the curve bends another way. In that case, the universe expands more slowly in the past and more rapidly later, so distant objects end up farther away than a decelerating model predicts. On a Hubble diagram, that shows up as supernova points sitting above the decelerating curve, faint by a few tenths of a magnitude, small in appearance, enormous in implication. In the late 1990s, 2 teams found the bend that should not exist, using different telescopes and different analysis pipelines. The Supernova Cosmology Project and the High Z Supernova Search Team Each assembled samples that reached to redshifts around 0.5 and beyond. They expected to measure how much the universe was slowing, and instead, they found evidence that it was speeding up. The historical context matters because the field was primed for disappointment. Earlier debates about the Hubble constant and the age of the universe had taught cosmologists to distrust single-number answers. Yet here was a pattern that persisted across objects, across telescopes, across methods, and across teams that competed as much as they collaborated. Least unbelievable is not the same as understood. The result implied a component with negative pressure, something that makes space-time expand faster as it grows. And it implied that most of the universe is something we cannot name. In Einstein's equations, pressure gravitates, and negative pressure can behave like a repulsive term on cosmic scales. That is a strange sentence, but it is the mathematical reason acceleration is possible. The simplest candidate is the cosmological constant, lambda, a uniform energy density of the vacuum. Historically, lambda was introduced by Einstein to hold the universe static, then discarded after expansion was discovered, and later resurrected by the supernova results. That arc is part of the mystery. A term once called a mistake returns as the best-fitting description of reality. Yet the cosmological constant comes with a problem that is almost embarrassing in its scale. Quantum field theory predicts vacuum energy from zero-point fluctuations, but naive estimates overshoot the observed value by many orders of magnitude. The mismatch is not a small discrepancy, but a chasm, and it suggests that something about our understanding is incomplete. Rubin enters this story with a different promise than earlier surveys, and the promise is discipline. It does not rely on a patchwork of fields, instruments, and selection rules that change from year to year. It builds one uniform, decade-long dataset that can be audited end-to-end, with a cadence designed to make time itself a controlled variable. Rubin's advantage begins with scale, but scale alone is not the point. The point is uniformity across the southern sky and across time, because uniformity turns unknown biases into measurable ones. When the observing strategy is consistent, selection effects become a function you can model, rather than a suspicion you can only fear. In the visuals, the survey strategy looks like a slow, methodical sweep. Night after night, the same fields are revisited, and the same stars appear again as calibration anchors. The camera's enormous field of view captures wide swathes of sky in a single exposure, and the repetition builds depth like layers of paint. Type Ia's supernova cosmology lives or dies on systematics, because the signal is subtle. You can be fooled by dust that reddens and dims light, especially if the dust properties differ from the Milky Way's average law. You can be fooled by evolution, if supernova progenitors at high redshift differ in composition or age from those nearby. You can be fooled by misclassification when a different kind of transient masquerades as a type 1a. You can also be fooled by Malmquist bias, the quiet preference for brighter events in a magnitude-limited survey. If faint supernovae drop below detection, the sample becomes artificially bright and the inferred distances shift. Calibration drift can do similar damage because a small tilt in photometric 0 points becomes a false tilt in the Hubble diagram. Rubin attacks those failure modes with repetition and consistency, and that approach changes what control means. It finds supernovae early, so light curves are sampled before peak, near peak, and well into the decline. It measures them in the same filters, with the same camera, and under the same calibration discipline that is applied to the entire survey. Early discovery is not just a convenience, because the rise time contains information. The shape of the early light curve helps distinguish type 1a explosions from core collapse events, and it constrains how the explosion ignited. Better sampling reduces the need for extrapolation, and extrapolation is where hidden biases like to hide. A decade of imaging creates enormous supernova samples across a wide redshift range, and the statistical power becomes almost unfamiliar. Nearby events anchor the low redshift end, where peculiar velocities, galaxies' local motions, add scatter to redshift-based distances. Distant events probe earlier cosmic time, where acceleration first becomes visible as a divergence from decelerating expectations. Large samples change the logic of trust because you are no longer hostage to a small number of rare objects. Instead of one best-fit curve, you can split the data many ways and demand agreement across subsets. You can compare supernovae in passive galaxies to those in star-forming hosts and test whether the environment changes the standardized brightness. Host galaxies matter because they are physical context, not just background scenery. Metallicity affects stellar evolution, and stellar age affects the distribution of progenitor systems, which can subtly alter explosion properties. If standardized brightness depends on host mass or star formation rate, Rubin's sample size makes that dependence measurable rather than speculative. You can test whether dust corrections behave with redshift the way physics expects, rather than the way a convenient model assumes. You can test whether light curve standardization drifts with host metallicity or stellar population age. You can test whether photometric classification biases the distance scale, especially when spectroscopy is scarce at the faintest limits. Rubin's supernova program is not only about more points on a plot. It is about controlling the selection function, because selection is the hidden hand in every magnitude-limited survey. Uniform cadence makes the hidden hand visible, so it can be modelled, corrected, and stress-tested. Even with perfect supernova distances, one probe is never enough, because cosmology is a game of degeneracies. Different combinations of parameters can mimic the same distance redshift curve, especially when uncertainties are correlated. Rubin's climax is that it does not ask one question once, it asks the same question 3 ways, and it demands that the answers agree. The question is the same across probes, and it is sharper than it sounds. What is driving acceleration, and is it constant in time? Is it a cosmological constant, a fixed property of space-time? Or is it a sign that gravity breaks on the largest scales? Type 1a supernovae measure distance and therefore geometry, because they map how far light travelled in an expanding spacetime. They are sensitive to the integrated expansion history, meaning they respond to the cumulative effect of the universe's expansion rate over time. In practice, they trace the shape of the Hubble diagram, a curve that encodes the cosmic scale factor's evolution. Baryon acoustic oscillations measure a standard ruler, and the ruler's origin is ancient. In the early universe, photons and baryons formed a hot plasma where pressure supported sound waves. Those waves propagated outward from overdensities until the universe cooled enough for electrons and protons to form neutral atoms, letting photons decouple and stream freely. When the photons left, the sound waves froze into the matter distribution, leaving a preferred separation scale. That scale is about 150 megaparsecs in co-moving units, and it appears today as a slight excess probability of finding galaxy pairs at that separation. The BAO feature is subtle, but it is robust, because the physics of the early plasma is well understood and tightly constrained by the cosmic microwave background. On screen, BAO is often shown as ripples, like rings expanding on a pond. The rings are not visible in any single galaxy map, but they emerge statistically when millions of galaxies are counted. Rubin's wide-area imaging provides the density field, while partner spectroscopy can sharpen redshift measurements, and together they turn that faint ripple into a ruler. Weak lensing and growth of structure measure how matter clumps over time, and they do it by watching shapes. As light from distant galaxies passes through the cosmic web, intervening mass slightly shears and magnifies the images. The effect is tiny for any one galaxy, but coherent across patches of sky, and it can be extracted by averaging over vast samples. Lensing tracks the competition between gravity pulling inward and expansion stretching outward. It tests not only geometry through distances that enter the lensing kernel, but also the strength and form of gravity, because growth depends on how efficiently matter can collapse. In a universe with strong late-time acceleration, growth slows, and the cosmic web becomes less dense than it would be otherwise. Each probe has its own weaknesses, and that is why the combination is powerful. Supernovae can be biased by dust and evolution, even when corrected, and their distances depend on calibration stability. BAO is robust, but needs huge volumes and careful modelling of galaxy bias because galaxies trace matter imperfectly. Lensing is direct to mass, but fragile to PSF modelling, blending, and photometric redshift errors. Growth measurements can be contaminated by baryonic feedback, where gas physics alters matter distributions on small scales. Intrinsic alignments can also mimic lensing, because galaxies can align with local tidal fields rather than being randomly oriented. Rubin's design is built to reduce these, then quantify what remains, because precision without error accounting is only confidence. The climax structure is a triangulation, and the geometry of that metaphor is literal. Supernovae draw the distance redshift curve, mapping how the universe expanded over time. BAO pins the scale of that curve with a ruler set long before dark energy mattered. Lensing and clustering test whether the same model predicts the observed growth of structure. If all three agree, the simplest story survives, and the universe looks eerily consistent. Acceleration behaves like a cosmological constant, and W stays near -1 within tightening uncertainties. If they disagree, the universe is pointing at new physics, and the disagreement becomes the most valuable data point of all. The equation of state parameter W is the compressed way to describe that physics, and it is deceptively simple. It is the ratio of pressure to energy density for the component driving acceleration, written as W equals P divided by rho. Matter has W near zero because its pressure is negligible compared to its energy density. Radiation has W near 1/3 because pressure is significant for relativistic particles. A cosmological constant has W equal -1, which is the special value that makes the energy density remain constant as space expands. In plain language, W tells us how dark energy's density changes as the universe grows. If W equals -1 exactly, the density stays constant per unit volume of space, even as that volume increases. If W differs from -1, the density evolves and the acceleration history changes. If W is greater than -1, the dark energy density dilutes with expansion and acceleration can weaken over time. If W is less than -1, a regime sometimes called phantom, the density increases as the universe expands, and the far future becomes more dramatic and less stable. A changing W is more than a number, because it would imply a dynamical ingredient rather than a fixed constant. It could point to a rolling scalar field, often called quintessence, whose energy changes as it evolves in its potential. In that picture, acceleration is a phase, not a permanent property, and the universe's fate depends on the field's dynamics. Rubin's role is to measure W with enough precision to make the distinction meaningful, and to do it without relying on fragile assumptions. It does this by extending the redshift lever arm and by reducing correlated systematics across probes. It also does this by measuring W as a function of time, not only as a single constant that averages away the story. Time variation is often parameterized as W0 and WA, a present-day value and a drift with scale factor. Rubin's decade does not change cosmic time directly, but it changes our sampling of cosmic history. It fills the redshift range with consistent measurements, so the inferred evolution is not stitched together from incompatible surveys. The tension is that W is not measured in isolation, because cosmological parameters are entangled. It is linked to matter density, curvature, neutrino mass, and the amplitude of primordial fluctuations. Degeneracies can make different universes look the same in one dataset, and that is why a single probe can mislead even when it is precise. This is why Rubin's multi-probe approach is the dramatic beat, not a technical footnote. Geometry probes, like Supernovae and BAO, can fit one expansion history, and many models can be tuned to match that history. Growth probes can accept or reject that history by checking whether structure formed as predicted, under the same assumptions about gravity and matter. Modified gravity can mimic dark energy in the distance curve, and that is a central danger. A change in gravity can produce the same expansion while changing how structures grow, because the field equations govern both the background expansion and the evolution of perturbations. That means decisive evidence must include growth and lensing, not only distances. In general relativity, the relationship between geometry and growth is specific, and it is testable. Given an expansion history, the growth rate of density perturbations follows from the gravitational law, and the two are locked together. If Rubin measures geometry and growth that cannot be reconciled, the law itself is suspect, and the suspicion is quantitative rather than philosophical. This is the modified gravity versus dark energy fork, and it is where the mystery deepens. Dark energy is new content in the universe, a component with negative pressure that changes the stress-energy budget. Modified gravity is new rules, where the same content behaves differently because the equations that relate matter to curvature are altered. Rubin's lensing maps are central to this distinction because lensing responds to the sum of gravitational potentials along the line of sight. Galaxy motions and clustering respond to another combination of potentials, connected to how matter feels gravity. In modified gravity, those combinations can differ, producing a gravitational slip that does not occur in standard general relativity. By comparing lensing, clustering, and redshift space information from partner surveys, cosmologists can test for that slip. Rubin supplies the wide-area lensing and the photometric redshift scaffolding that makes the comparisons possible. The combination can reveal whether gravity is consistent across scales or whether it quietly changes its behavior in the cosmic outskirts. Growth is also measured through how clustering evolves with redshift, because the cosmic web is not static. If acceleration is due to a cosmological constant, growth slows in a predictable way at late times, as expansion wins the tug of war. If growth is suppressed more than expected, it can imply new physics like massive neutrinos, which free stream and wash out small-scale structure. If growth is enhanced relative to the distance curve, it can imply a different gravitational strength on large scales, or a modification that boosts clustering. Either direction is a clue, but only if systematics are controlled well enough to trust the sign. At Rubin's precision, a tiny calibration error can masquerade as a profound physical effect. This is where cosmic variance becomes a character in the story, because it is a limit set by the universe itself. Even a perfect instrument faces the fact that we observe one universe, not an ensemble of universes to average over. On the largest scales, there are only a few independent modes in our observable volume, and their randomness limits precision. Rubin's survey design fights cosmic variance by surveying huge volume, because volume is the only antidote. Repeated imaging of the whole southern sky is not only for transients and time-domain surprises. It is for statistics, because wide area reduces sample variance in clustering and lensing, and it makes rare structures less rare. Wide area also stabilizes calibration, and calibration is the quiet foundation under every cosmological inference. If you observe many fields with the same strategy, you can cross-calibrate using overlaps and repeated stars. You can detect spatial patterns in photometric zero points that would otherwise masquerade as cosmology, especially when the signal is a slow drift with redshift. Uniformity is the hidden theme of Rubin's cosmology, because non-uniform surveys create false evolution. If selection changes with sky position, depth, or seeing, it can imprint patterns that look like redshift dependence. Rubin's cadence makes the selection function smoother and easier to model, and that modeling becomes part of the scientific result. The data to discovery pipeline is part of the climax because precision is built, not found, and it must be built repeatedly. Raw images are corrected for detector signatures like bias, dark current, and flat field variations. Optical distortions are modeled so that positions are consistent across the focal plane, and astrometric solutions tie the sky to a stable reference frame, Photometric calibration is equally exacting because magnitudes are the language of supernova cosmology. Atmospheric transmission changes with water vapor and aerosols, and the instrument's throughput can drift with time. Rubin's calibration plan uses standard stars, repeated observations, and careful modeling so that a magnitude measured in year 1 matches a magnitude measured in year 10. Difference imaging produces transient alerts, and in the visuals, it looks like subtraction magic. A new point of light appears where none existed in the reference image, and the pipeline flags it within minutes. Yet cosmology depends on stable catalogues, not only on alerts, because distances and redshifts require consistent photometry across many epochs. COADs build deep reference images that reveal faint galaxies and improve shape measurements. Forced photometry measures fluxes consistently at known positions, even when objects are faint or blended. That consistency matters because selection biases often enter when detection thresholds vary, and forced measurements reduce that variability. Photometric redshifts are estimated from multi-band colors, and their uncertainties are propagated rather than ignored. A galaxy's color is a crude spectrum shaped by stellar populations and by the redshifting of spectral features. Small biases in photometric redshifts can shift lensing kernels and BAO measurements, so Rubin's analyses treat redshift uncertainty as a first-class parameter. Shear catalogues are produced with PSF models that vary across the field and across time, because the atmosphere and optics blur images in complex ways. If the PSF is mismodeled, galaxies can appear slightly stretched in a preferred direction, and that false shear can mimic lensing. Rubin's repeated observations help because the PSF changes from visit to visit, allowing statistical separation of sky signal from instrumental imprint. Every step carries error models because error is the currency of inference, and the documentary's tension depends on that honesty. When the signal is a percent level tilt in a curve, confidence must be earned through accounting. The pipeline does not merely output a number, but a number with uncertainties, covariances, and traceable provenance. Reproducibility is not a slogan here, because the history of precision cosmology is a history of subtle mistakes. It is the defense against self-deception when the desired answer is tempting and the data are complex. Rubin's data products are designed to be reanalyzed by the community, with documented pipelines, versioned calibrations, and public releases that allow independent checks. Open data products widen the net for mistakes and for insight, and that openness changes the sociology of discovery. Independent teams can rerun analyses, try different systematics treatments, and attempt to break the result. If the conclusion survives adversarial scrutiny, it becomes harder to dismiss, and it becomes a foundation rather than a headline. Community science also matters because Rubin's datasets are too rich for one collaboration's imagination. New cross-correlations will be invented after the data exist, because methods evolve when data force them to. Dark energy constraints will improve as techniques mature and as external datasets join, tightening the triangulation that the chapter has been building toward. The narrative tension rises as the probes converge, because convergence is not guaranteed, and agreement is not automatic. Supernova distances could prefer 1W, especially if dust or evolution is mismodeled. BAO could prefer another, especially if galaxy bias is misunderstood, or if redshift distributions are misestimated. Lensing growth could prefer a third, especially if shear calibration or intrinsic alignments are not fully controlled. If Rubin finds that the probes disagree beyond known systematics, the story changes abruptly, and the change is the point. It could mean hidden biases in photometric redshifts or shear calibration, the kinds of errors that hide in plain sight. It could mean supernova evolution that standardization did not capture, a slow drift that only a decade-long uniform survey can reveal. Or it could mean that the model is wrong in a deeper way, and that is the unsettling possibility. It could mean W is not -1, and the vacuum is not acting like a simple constant. It could mean W changes with time, implying dynamics in the dark sector. It could mean gravity is not general relativity on the largest scales, and the equations we trust are approximations. This is the chapter's climax beat, and it is a different kind of impossible. The impossible thing is not a single object, but a contradiction that persists after every calibration check, every null test, and every split sample analysis. A contradiction would be the universe forcing theory to choose, and forcing us to admit that our elegant model is incomplete. The documentary's hook returns in a sharper form, because the sky is not a still photograph. If the sky is a live feed, then acceleration is not a static parameter to be looked up in a table. It is a history written across billions of light years, and Rubin is watching enough of the feed to read it with statistical clarity. The stakes are existential in a scientific way, because the far future is an extrapolation of the physics we measure now. A cosmological constant implies a universe that expands faster forever, with galaxies fading beyond the horizon and the night sky growing emptier. A changing dark energy could slow, stop, or reverse, reshaping the far future in ways that are difficult to picture and harder to test. Even if the ending is far away, the physics is present now, and it connects to the deepest theories we have. Vacuum energy connects cosmology to quantum field theory, where naive calculations overshoot by absurd factors and demand explanation. Modified gravity connects to attempts to unify forces and to build a consistent theory that reproduces Einstein locally while changing behavior cosmologically. Rubin cannot solve the vacuum energy problem directly because it is a theoretical puzzle about cancellations and symmetries. Yet it can constrain the behavior tightly enough to corner theory, and corners are where progress happens. If W is exactly -1 within small errors, many dynamical models become strained and finely tuned. If W deviates, the cosmological constant becomes less plausible as the whole story. The chapter's final movement is a controlled escalation, with each probe tightening the net. Rubin measures supernova distances with unprecedented uniformity, reducing the chance that selection bias is doing the talking. Rubin measures BAO across huge volumes to anchor the distance scale with an early universe ruler. Rubin measures lensing and growth to test gravity's consistency, where modified laws would reveal themselves. Then Rubin asks the only question that matters at this precision, and it is asked without drama in the mathematics and with drama in the consequences. Do these three stories describe one universe, or do they describe three incompatible ones? Are we seeing a single coherent expansion history, or a patchwork that hints at missing physics? If they align, the universe is eerie in its simplicity, and fate looks like endless acceleration, a quiet thinning of the visible cosmos. If they do not, the universe is strongest than the simplest model, and the cracks point toward new fields or new gravity. Either outcome is a revelation, because either outcome tells us what kind of universe we inhabit. Transition. While Rubin tests the fate of the cosmos, another mystery tightens closer to home. In the outer solar system, distant orbits may align as if something unseen is shepherding them. That alignment could be selection bias, the same enemy Rubin was built to defeat, wearing a different disguise. Or it could be a planet-sized mass in the dark, rewriting our map of the solar system. The next chapter follows that nearer shadow. We return to the solar system's edge, where sunlight thins and maps become provisional, and even familiar constellations feel like a backdrop rather than a destination. Beyond Neptune, the Kuiper Belt and scattered disk hold bodies that never fully joined the planets, leftovers from construction sites that never quite closed. In wide shots, this region looks empty, but the emptiness is deceptive. Its inhabitants are simply small, dark, and far away. Many are coated in irradiated ices and complex organics, the kind of surface chemistry that reddens under cosmic rays and ultraviolet light. Their temperatures hover only tens of degrees above absolute zero, where water ice is rock hard and methane can behave like a mineral. Their orbits are not just paths, they are archives of early migration and chaos, written in angles and distances rather than in words. When the giant planets shifted in the solar system's youth, their gravity swept resonances outward like moving grooves in a record. Objects caught in those grooves were carried, scattered, or protected, and some still bear the imprint of that long-ago rearrangement. Resonances with Neptune, tilted inclinations, and stretched perihelia preserve ancient pushes, pulls, and near misses, even when the bodies themselves are too small to remember anything. A resonance is a repeating gravitational rhythm, a pattern of orbital periods that makes small tugs add up over millions of years. It is slow physics, but it is decisive physics, and it can keep a fragile orbit intact. Some objects are extreme, with perihelia far beyond Neptune's direct control and semi-major axes hundreds of AU long, so their years become millennia. They spend most of their time in deep cold, moving slowly against crowded starfields, and then briefly swing inward like a pendulum returning to a familiar point. In visual terms, they are almost motionless, just a faint dot that shifts by a fraction between nights. This is where the Planet 9 hypothesis enters, not as certainty, but as a testable claim, and it arrives with the quiet drama of a pattern that should not be there. A subset of extreme trans-Neptunian objects appears to share similar orbital orientations, as if shepherded into alignment. The claim is not that every distant orbit is strange, but that a particular kind of strangeness repeats. Orbital orientation is a technical phrase that hides a simple idea: which way the long axis of an orbit points, and where the orbit is tilted relative to the planet's plane. Astronomers track angles like the argument of perihelion and the longitude of the ascending node, because those angles precess under gravity like a spinning top. If many objects share similar angles, something may be organizing that precession rather than letting it randomize. The proposed cause is a distant planet on an eccentric, inclined orbit that stays far beyond Neptune, spending its life in the dark between stars. Plausible ranges are broad, perhaps several Earth masses, perhaps hundreds of AU away, perhaps taking millennia to circle. The uncertainty is part of the story. An unseen planet can be inferred only through the fingerprints it leaves on others. If such a planet exists, it could corral long-period orbits, raise perihelia, and tilt populations into unusual planes, turning a scattered set into a structured family. Over time, repeated gravitational nudges can lift perihelia so objects stop approaching Neptune closely, which helps preserve their strange configurations. It could also create new resonant families that a uniform survey should reveal, because resonances do not hide forever once you have enough examples. But finding it is brutally hard, because distance turns mass into faintness and time into patience, and the sky does not volunteer its secrets. Reflected light drops fast, while the planet's apparent motion becomes a slow drift, not a streak, and the human eye is trained to notice streaks. At hundreds of AU, even a large body can be dimmer than the background of unresolved galaxies. The physics of faintness is unforgiving. Brightness falls roughly with the fourth power of distance when you rely on reflected sunlight, because light must travel out and back. That means doubling the distance can make an object about 16 times fainter, even before you account for a dark surface. In practice, a planet could be present in images and still be indistinguishable from noise without careful, repeated measurement. The search area is huge because the orbit is unknown and the sky is large, and the best guesses still span thousands of square degrees. A planet near aphelion could hide in plain sight, dimmer than many galaxies and moving less than an arc-second. In a static frame, it would look like a star, and in a crowded field, it could be lost among them. Previous surveys were deep or wide, but rarely both, and their cadence was uneven by necessity. shaped by weather, telescope time, and competing priorities. Gaps in coverage, changing filters, and shifting selection functions can manufacture patterns that look physical, especially when discoveries are sparse. A discovery is not just an object, it is an object plus the circumstances that allowed it to be noticed. Even when images exist, linking detections across months is computationally hard without a consistent strategy, because the number of possible pairings explodes. A slow mover can be misclassified as a star, a galaxy, or a subtraction artifact, and then quietly discarded by automated pipelines. The outer solar system punishes shortcuts because its signals are weak and its timescales are long. Rubin changes the hunt by making repetition the default rather than the exception, and by treating time as a core dimension of the survey. It images wide fields deeply, then returns again and again, building a time baseline that turns motion into evidence. Visually, the same patch of sky becomes a flipbook, where the background holds steady and the solar system shifts. With many visits, faint points can be recovered through stacking and forced photometry at predicted positions, pulling a signal out of the noise without pretending it is brighter than it is. With many seasons, orbit fitting becomes stable, and false linkages can be rejected statistically because wrong solutions fail to predict future positions. The method is patient. It lets the sky reveal itself through consistency. Rubin's completeness matters as much as its depth, because Planet 9 is a population problem first, and populations require fair sampling. If the clustering is real, many more extreme objects should exist, and Rubin should find them, not just the easiest ones. A larger sample turns a suggestive alignment into a measurable distribution, with uncertainties that can be stated plainly. If the clustering is bias, Rubin should break it by observing uniformly across longitudes and ecliptic latitudes, including regions others avoided. The same dataset that finds candidates also measures the selection function that could fake them, because you can model what the survey would have found. In science, the ability to quantify what you missed is almost as powerful as what you saw. Alternative explanations remain credible, and the chapter keeps skepticism as a discipline, not as a mood. The apparent alignment could be small number statistics, where a few discoveries over-influence the story, and coincidence masquerades as structure. When the sample is tiny, every point looks like a trend, and every trend feels like a clue. It could be observational bias, because surveys often search where follow-up is possible, and where the Milky Way is quieter, with fewer stars to confuse detection. It could be the collective gravity of many small bodies, a distributed disk that nudges orbits, not with one dominant hand, but with a broad, persistent pressure. That idea trades a single hidden planet for a hidden mass budget spread thinly across space. It could be a past stellar flyby, when the Sun was young in a birth cluster and encounters were closer, and the solar system's outskirts were easier to disturb. A passing star would not need to capture anything. It would only need to tug, briefly but decisively, on the most distant debris. It could be a distant companion in the Sun's early environment, now long gone, leaving only a dynamical scar. Each alternative predicts different signatures in the broader orbital distribution, and Rubin can test them with the kind of sample size that turns arguments into calculations. A planet implies resonant structure and specific correlations in argument of perihelion and node, including patterns in how those angles cluster or anti-cluster. It also implies a relationship between inclination and perihelion distance that should repeat across many objects. A massive disk implies smoother trends and different inclination distributions, without a single dominant perturber imposing a preferred direction. A stellar encounter implies a different pattern of perihelion lifting and a different sky anisotropy, because a flyby has a direction and a timing. The outer solar system becomes a forensic scene, and the orbits are the evidence. The point is not to defend a favourite explanation, but to demand predictions that survive new data. especially data gathered without special pleading.
Rubin's decade makes the outer solar system legible as a statistical system, not a rumor, and it makes disagreement productive rather than personal. When the dataset is shared and the biases are measured, the debate becomes about physics. Transition. After measuring cosmic acceleration, we come back to a nearer darkness that still shapes our own neighborhood. The central question returns in miniature, because Planet 9 is another invisible sculptor, and the scale shift does not change the logic. We ask again what is shaping trajectories, and whether the cause is mass we missed or bias we built. In the outer solar system, gravity is gentle, but its effects accumulate until they look like intention. This echoes the earlier chapters where motion separated asteroids from noise and light curves separated explosions from artifacts, and where statistics turned weak signals into strong conclusions. The method is the same, even when the scale changes by orders of magnitude, because the universe keeps speaking in patterns. The challenge is learning which patterns are real and which are artifacts of how we look. Rubin's alert stream is not only for supernovae and flares, it is for slow movers too, and it treats them as first-class events. Nightly differences flag candidates, pipelines link tracklets, and community follow-up turns hints into orbits, tightening uncertainties night by night. A faint dot becomes a trajectory, and a trajectory becomes a test of competing models. The sunward blind spot remains, and Rubin cannot erase geometry or daylight, because no ground telescope can watch through the sun. Some hazardous objects still approach from near the sun, requiring infrared space surveys and twilight strategies to close gaps. The edge of the map is not only far away, sometimes it is hidden by glare. Yet the broader lesson holds, because Rubin reduces the unknowns by making absence measurable, and by turning "we didn't look" into "we looked and didn't see." When coverage is uniform, what is not seen becomes information, not just a missing page. Limits become numbers, and numbers become constraints on mass, distance, and reflectivity. If Planet 9 is found, it rewrites the solar system's inventory and explains a set of strange orbits, and it forces a new chapter in how planets form and migrate. It would raise a historical question as well. How did a multi-Earth mass body end up so far out, and why did it stay? The answer would connect dynamics, formation models, and the early environment of the Sun. If it is not found, the non-detection still constrains mass, distance, and sky location, shrinking the parameter space where it can hide. It also pressures alternative explanations to become quantitative, because the data will no longer tolerate vague possibilities. A missing planet can still teach you what the solar system is not. Either outcome is a result, because it turns a speculative pattern into bounded physics, and it replaces a rumor with a confidence interval. The map's edge moves outward, and the uncertainty shrinks into numbers that can be argued with. In that sense, the discovery is not only an object, but a reduction in ignorance. Now we resolve the documentary's impossible claim, and it is not one object at all, not even a planet that headlines the news. The impossible feat is turning the sky into a continuous, comprehensive, time-aware dataset, where every patch is revisited and every change is logged. It is a shift from occasional glimpses to systematic memory. Old astronomy lived on frozen frames, stitched catalogues, and selective follow-up that hid selection effects, because the gaps were invisible to the people reading the results. Rubin makes time a coordinate, so change is captured systematically rather than accidentally, and so calibration is part of the story. The survey does not just collect photons, it records context. Across the series, that strategy links near-Earth hazards, transient explosions, dark matter maps, and dark energy tests, and it does so with the same underlying cadence. The same cadence that finds a faint asteroid also calibrates shear, distances, and growth, because it repeats measurements until they become reliable. The repetition is not redundancy,
It is how uncertainty is tamed.
Rubin's real discovery is the universe as a changing system, where gravity and expansion leave fingerprints in motion and statistics, and where the unexpected is not an exception. It does not promise one headline. It promises a decade-long movie with audit trails, where claims can be replayed and checked. In that movie, even the slowest drift matters. The cold open anomalies are answered in spirit, even before any single explanation is named, because the pipeline turns ambiguity into classification. A shifting point becomes an orbit, a brief brightening becomes a classified transient, a vanishing source becomes a measured limit. The mystery does not disappear, but it becomes measurable. What once looked impossible becomes routine, because the gaps are gone and the pipeline remembers, and because the same sky is seen under many conditions. The sky is no longer a postcard. It is a record of events, trajectories, and slow drifts, annotated by time. And with that record comes a quiet challenge. What else has been there all along, waiting for persistence? Final beat. The first images are not an ending. They are the start of a new kind of knowing, where the night is monitored with disciplined attention. The secrets now must hide in plain sight, inside a live feed that never stops watching, if they can. Across this journey, the biggest revelation wasn't a single spectacle. It was the sky's constant restlessness, finally measured instead of merely noticed. We watched how old astronomy, built from stitched still frames, missed the brief flares, the subtle shifts, and the faint movers that live between observations. Rubin changes the rules by making time a first-class coordinate, pairing a wide field with relentless cadence, and turning the southern sky into a decade-long, calibrated record of change. That engineering, Seropachon's steady nights, an 8.4-meter mirror feeding a car-sized camera, optics that keep the edges honest, and pipelines that treat calibration like truth, creates a new kind of instrument. It is not just a telescope, but a survey engine that can revisit, subtract, and alert night after night without forgetting what it saw before. In that stream, the first shocks arrive close to home, where faint asteroids and comets hide in noise, smear into streaks, and slip in from geometry's blind angles near the sun. Rubin cannot erase every sunward gap, but it can shrink the unknowns, link photons into orbits, and turn planetary defense from patchwork discovery into statistical patrol. Then the background starts to blink, and the universe stops pretending it is still. Supernovae rise before our eyes, kilonovae fade from blue to red, black holes flare as they feed, and quasars flicker with the delays of light echoing through accretion disks. The flood is too large for humans alone, so classification becomes an ecosystem. Difference imaging, machine learning triage, and follow-up networks that decide, within minutes, what deserves deeper attention. In the same decade-long ledger, Rubin also measures the quietest signal of all, the percent-level stretching of galaxy shapes that reveals the dark scaffolding, and the distance, redshift story, that tests whether cosmic acceleration is truly driven by a constant lambda or something stranger. Even at the solar system's edge, Rubin's promise is the same: persistence over anecdotes. If extreme trans-Neptunian orbits really do align, uniform sampling and a measured selection function will make the pattern survive scrutiny, or collapse as bias. If Planet 9 exists, Rubin may not just spot a faint drifting point, it may prove an unseen mass by the choreography it forces on distant worlds. If it does not exist, Rubin's census will still tell us what did the sculpting: an ancient flyby, a distributed disk, or migration scars written into resonances. And that returns us to the unresolved, impossible moment from the beginning. The point that shifted, the brief brightening, the star that vanished. Under old observing rules, each could be dismissed as an artifact, a cosmic ray, a calibration slip, a once-in-a-lifetime coincidence with no context. Rubin's cadence is the context, because repetition turns a suspicious blip into a light curve, a track, a population, or a null test that refuses to lie. The impossible thing Rubin captures is not a rule-breaking object, but time itself, woven through the sky so densely that the invisible must leave fingerprints, or be forced to change its story. In practice, Rubin's decade will be a continuous argument with the universe, one that systematics cannot easily win. If a shear pattern persists across filters, seasons, and independent calibrations, it becomes a map of mass we cannot see. If supernova distances, BAO geometry, and growth of structure all agree, dark energy tightens into a number. If they disagree, the cracks point to new physics, or to the limits of our assumptions. The same logic applies to the alert stream, where rarity is not enough, because only repeatability and cross-checks can separate discovery from mirage. So the main threads converge into a single claim, earned the hard way. Motion is evidence, change is data, and patience is a measuring instrument. Rubin's power is not that it looks deeper once, but that it looks again and again and again, until the universe either repeats itself or admits what has been hiding. In that sense, the documentary's mysteries do not end unresolved. They end reframed. The anomalies from the cold open are no longer isolated riddles. They are prototypes of a new measurement culture, where every suspicious photon is interrogated by the next night sky. Rubin will not guarantee a single headline, but it will guarantee a verdict on whole classes of possibilities, because a decade-long movie leaves fewer places for the cosmos to hide. The result is a kind of closure that science rarely offers in one dramatic reveal. If dark matter is cold and collisionless, the cosmic web should sharpen in predictable ways, and Rubin will see it. If it is warm, fuzzy, or self-interacting, small-scale structure will soften, halos will core, and Rubin will see that too. If dark energy is a constant, the expansion history will stay smooth. If it evolves, the universe's past and future will diverge in measurable, uncomfortable ways. And yet, even if every parameter lands exactly where today's models expect, Rubin still delivers something profound. It turns the night sky from a museum into a living system, and it makes our ignorance quantifiable rather than poetic. The impossible thing is not that the universe broke its rules, but that we finally built a way to watch the rules being written in real time. Call back to the opening question. When we watch the entire sky change for a decade, will Rubin expose what is really shaping the universe? The honest answer is that Rubin may not name the culprit in one stroke, but it will force the invisible to testify, through gravity's distortion, through expansion's geometry, and through the motions of worlds we cannot yet see. If dark matter and dark energy are real substances, their fingerprints will accumulate until denial becomes harder than belief. If they are placeholders for deeper laws, Rubin's movie will show where the placeholders fail. In the cold open, we asked what else has been changing in the dark while we weren't looking. Now we can say the more unsettling thing. The sky has always been changing, and the only impossibility was thinking we could understand it from still frames. Final thought. A decade from now, the most important image Rubin gives us may not be a picture at all, but a timeline. In that timeline, every flare, drift, lensing shear, and dimming distance becomes a syllable, and together they spell out what the universe has been doing, quietly, continuously, since long before we learned to watch. Call to action. When Rubin's alerts and data releases arrive, follow them, support the networks that verify them, and let the universe's moving story belong to more than a handful of eyes. The impossible thing Rubin captured was not a single forbidden object, but the sky's missing dimension, time, measured densely enough that dark matter, dark energy, and hidden worlds must leave repeatable fingerprints. Watching the whole sky change for a decade won't just answer our opening question, it will narrow the universe to a few explanations that can no longer hide behind gaps.
In the end, Rubin doesn't promise one perfect photograph. It promises a decade-long movie where gravity, light, and motion cannot help but confess. If the universe ever broke its own rules, this is how we will finally catch it, by watching long enough to learn what its rules really are. When the alert stream goes live, pay attention, share it, and support the follow-up science, because the next impossible signal may need all of us to recognize it.